So you struggle to articulate it might be recorded. So, but that's okay. Fire away.
That, all right, so this goes back to the antenna that you shortened with the coils so that
Uh-huh.
you could physically put it in your yard or
Yep.
wherever. So the waves, the wave it's trying to encounter is not it's not that length that we've made it. It's longer. So, I mean, this is really just a question about the energy. How does it's not that long anymore. I mean, it is
It
with the
it
coil.
is, but it isn't. So
Yeah.
so what
So
what so what
what
do
does
you
the wave
sus
have to do to encounter that?
well, it will still encounter it, but what's going to happen? I mean, what do you suspect is going to
I don't
happen?
know. In my mind, the wave has to contort itself to
Yes. Okay.
encounter.
Yes, and if the wave has to contort itself, what's going to happen to the energy?
Well, it seems like it would change, like it would
Yes.
change frequency or change
No, you can't.
amplitude.
You can't
It
change
can't.
the. You can't change frequency. Frequency is intrinsic to the wave itself.
I know. That's why
So
I'm
what?
asking.
But
Like,
what does
well,
change? You just said it.
the amplitude?
The
The,
amplitude, because the incoming wave. If you're looking at receiving versus transmitting, the incoming wave generates a voltage and current in a piece of wire, which is then sent down to the receiver. Right. So if what it really comes down to is
N7JI
whether or
Technician.
not you believe that particular piece of wire is an efficient thing for resonating, being driven by that outside wave. What do you,
what you said, I have that is gobbledygook to me.
no,
I,
no, no,
I'm
no.
just,
If I if I take something and let's say it's a let's say let me try to get a good analog. Okay, so what I'm going to do is I'm going to do my first share of the day. Okay, so if this is a half wave, right? The wave is coming in. It's a half wavelength long because it's actually going this way or it's going this way. It doesn't really matter at this point. If it matches and the waves coming in is the right length wave for this, what will happen is it will deliver maximum energy to the antenna. What is the job of the antenna? I mean, fundamentally, what's the job of the antenna? What does it
is to
do?
grab the wave because there's so many
Or,
waves.
yes, okay, but grab it. What does it do with it?
And then it sends it down and it demodulates it so we
No, it doesn't do any demodulation. What does
the
the.
wave doesn't, but our equipment does.
Yes, but that's not important.
All
We're
right.
just talking about the antenna. What's the job of the antenna? It's to convert a wave which is traveling in space into current. That's it.
Okay.
That's its job.
Okay.
That's it. Okay, so if it encounters an antenna that instead of that long is let's say only this long, is that antenna going to do as good of a job remembering that the endpoints have to be at zero current, which means that your maximum is only now this big? Is that antenna going to do as good of a job?
So you're telling me I am at ground zero here, Scott. So
So,
my
yep,
questions are so basic.
yeah,
So you're telling me that my antenna still encounters this wave, but it
sure,
only encounters a portion of the wave. So
right,
I'm getting the full energy of the wave. Is that correct?
yeah. It's doing the best that it can, which
Okay,
is which is not very good if
which is
it's the
not very
wrong
good. But
length.
now make it that coiled up, that shortened, physically shortened, but it's still as
Okay,
long as the half wave.
okay. This is actually a really good question.
Oh, good.
Yeah. And so basically, that antenna, if you want to think of it this way, with the coils, it is still electrically the same length as the full size antenna.
Yeah.
So what happens when a wave comes along that is this long? is that,
This is my question.
so basically this section, right? If you want to match it up, this section fits on there, and then this section fits right here, and this section fits right here. Electrically, this whole section fits into the coil area, but the problem with the coil is if I draw a microscopic view of how the coil is laid out, essentially it looks like this, right? If I have two pieces of wire and they're carrying a current and they are in phase with each other and they look like this, they add together if they're spaced very close together. But if I draw the current on this piece of wire, I'm going to use brown, it'll look like this. And then it'll jump across this and go here, and then it'll be here for this section. But then it encounters this other section, right? And it's already on this side, and now it's over here, and then it's up here, and then it's down here, and then this is here, and this is here, and this is here. And what happens in that area right there?
I don't think I understand your diagram. What is your diagram?
This is current. The red is the wire, and the brown is the current. And
Yeah,
the current is a movement of electrons because that's what makes a field happen.
I
If
don't understand your wire.
I'll make it bigger.
I
I mean,
don't know that you.
this is the curled up portion of the antenna. That's a big view of the curled up portion of the antenna. It's easier to think of an antenna as being a transmitting antenna rather than a receiving antenna. It turns out that it works the same both ways. So in this area, if I have a straight wire, right, which I'll draw like this, my current is going to be smooth and it's going to be fairly uniform. It's going to be like in the positive direction, and this would be the negative direction. So in that one area, it will be positive, and then it might switch to negative, but that doesn't matter. We're just going to look at it in the positive direction, right? So this is the wire, and the brown is the current. That current is all moving in the same direction. But now we're going to take this wire and we're going to crunch it all up. We're going to
Well, we
take,
haven't crunched it. We've coiled it, and
no,
that's what
we've crunched it. Think of it as crunching it. Ignore the coil.
ignore the coil.
Ignore the fact that it's a coil, because this is basically what a coil does. It crunches up the wire and it makes it double back on itself. Okay, so now if I draw the current here, it's still in the positive direction. But then it gets to this piece of wire right here, and the wire has now turned, so the positive direction is here. The wire bends, right?
Hmm.
Positive is still positive. It gets to this part right here, and now it's here. And then it gets to here, and it's over here. This is the positive direction. And then it gets up here, and this is the positive direction. And then it gets to here, and this is the positive direction, because the wire basically sees the positive direction as to one side of it. So you now have these currents that are essentially following the wire. In this section right here, and in this section right here, those currents are now opposite each other, aren't they?
They don't like each
They don't
other.
like each other. They each generate an electric field and a magnetic field, but they are traveling in opposite directions. So what happens to the fields that they make?
Cancel
I
it out.
don't.
They cancel each other out. They're opposite. They're equal and opposite, and they cancel
Okay,
each other out.
you just lost me. They
Why?
don't look opposite to me. They're both positive.
They're
They're,
not. They're not. If you now look at this from the outside world, this one is going this way, and this one is now going this way. Those are
okay,
opposite directions.
they're opposite directions. Why does that matter?
Hold up your hand. Right hand rule. Take your thumb, that's the direction of the current, and do this. And notice that it rolls. You have to do that. You have to roll your hand forward.
Right. So this is
But
the
now
A.
turn it around because it changes direction and roll your hand the other way. And you add this and this, and what do you get?
I am not making this leap.
Hold up
It's
your hand. You gotta do this part. Ready? Now roll your hand forward. Roll your fingers forward. Okay? You rolled them forward, right? Now flip your hand around and roll your fingers forward. What
so
direction?
what?
They You
It,
add this together to this, and what's the net result?
why does it add together?
Because they both exist. They have to exist. If you look at this, they're in the same place. Right there. They're in the same place, so they add together. Their impacts add together. Those
There's some technical there. I don't understand this piece.
those
Yeah, yeah.
does
It's me.
this okay,
Which I don't understand either.
does number okay, here. Does
This
the
is current. This isn't a magnetic field, right?
Yes, it is a magnetic field.
It is a
Yeah. Does the
okay.
does the magnetic field made by number 1 here know
Okay.
anything
It's
about the
because
mag?
it's the magnetic field
Yeah.
that you're talking about. Not okay. There's current and there's magnet. Ugh.
So does the current, which is represented by number 1, know anything about the current that is represented by number 2? No. They opposite. Does the magnetic field made by number 1 know anything about the magnetic field made by number 2? Once
Yeah,
they
they're
No.
both they don't like each
Once
other.
Yeah, but once they leave the antenna, do they even know about each other? No. You just know that this one is positive and this one is now negative because it's in the opposite direction because it's made from a current flowing in the opposite direction. And now you get a plus and a minus. This part of the antenna does nothing.
Okay, so you just said an important thing.
Okay.
When the current is flowing, when you've got current flowing in opposite directions, that one is positive and one is
Well,
negative.
that's why I had you do this. You wrap your
No, that
hand.
doesn't, sorry, it doesn't work for me. It's meaningless.
Okay.
Okay. Uh, but because of the magnetic field, the current creates this magnetic field, and it is just a directionality in a magnet, in a magnetic field.
If
So
you
when
want to
it
think of it that
flows
way,
through a magnetic field, if it's going in opposite directions,
they
then one
cancel
side
each
is
other.
positive, one is negative. Okay, I can barely grasp that, but I've got it tenuously.
Well, the other way to think about it is take one hand and move it this way, and then take the other hand and move it this way. Right? Where's the center?
My
It's
hands
right
aren't
where it started.
magnified.
Right where it started. So it effectively does nothing. When you kink a piece of wire in that area, the wire does nothing.
So, okay.
Except it's still carrying current. It still makes the laws of physics have to work. So the antenna is still the right electrical length, but it's now the wrong physical length, which basically means that it's not efficient in doing its job. It still works, but you've just killed the efficiency. So you're basically trading efficiency for space.
But somehow coiling it is more efficient than not coiling it
Oh
and leaving
no, not at
it.
all. Coiling
No.
it is the same thing as kinking it back on itself.
So why are we doing this?
What if you have a 130-foot antenna and you want to make it fit in 50 feet?
Well, yeah, you're coiling it. Why am I doing that if it's not any more efficient than just having a shorter straight
It
wire?
is more efficient than having a shorter wire.
Okay, you're gaining something.
You are gaining something. It's still the right electrical length, so at least it works. It doesn't work as well as if you stretched it all out, but it's better than nothing.
Okay, okay. You've answered the question.
Okay, good. See, remember I said that I thought it was a good idea to ask questions because, it makes me think of things in different ways. It makes everybody cannot be the only person who's wondering about something. So, all right. Other questions before we go? Nobody? Okay. I find that hard to believe, but here we go. All right, so today We are going to finish the whole thing. Okay, so today we are into feed lines and connectors. We did feed lines kind of already. Does everybody remember what the difference between resistance and impedance is?
Yes.
All right, let's hear it. Somebody tell me.
Resistance is like you say, holding your thumb over an end of a garden hose or pushing a sofa across the living room, and impedance would be the magnetic field effect.
Yeah, basically resistance is something's ability to block the flow of DC. Impedance is the ability of something to block the flow of AC. That's the easiest way to remember it.
That makes a lot more sense.
And they're both measured in what units?
Ohms.
Ohms. Yeah, that's not confusing at all.
Well, this is ohms. Okay, yeah.
Everything's in ohms. And in fact, the other thing is that reactance is really the ability of something, how it behaves in the presence of AC, of different frequencies. All right. So, good job. Good job. And while I pull something up here, has anybody had any good success working on practice exams in the last day
Yes.
that they hadn't before?
Even this morning.
Yes.
Let's hear what you got out of yesterday.
We address the
What,
math.
what
The math is a good portion of it. Some of the legal stuff that I'm completely unfamiliar with, I've gotten down a lot better. I
Okay.
still need to go over it several times because even taking the practice test last night, I failed it, but I'm a lot closer.
Okay, good.
That site has flashcards. Those were really useful.
Okay, the ham study. Okay, so while we were talking about that, I pulled this up. Okay, remember I mentioned something about coaxial cable and the fact that coaxial cable behaves differently at different frequencies and for different sizes?
Yes.
Okay, notice this is decibels per 100 feet. Now everybody understands decibels, right? 3 decibels is how many times?
2 times.
2 times. And 10 decibels is 10 times. Okay, so let's take the very popular RG58. This is what you typically use for, for low power stuff. Notice that at 7 megahertz, you lose 1 decibel per 100 feet. That's not much. Now raise that up to 50 megahertz. How much do you lose?
Oh,
3 decibels. Basically 3 decibels. At 3 decibels, if you put in 100 watts, how much power do you get out on the other end? What does 3 decibel mean?
Double.
10 to the third.
50.
No. 3
No?
decibels is half or 2 times, whether it's plus or minus. If it's loss, it's
Oh.
negative.
Okay.
That is the fundamental thing that I want you guys to come away with. 3 decibels is how many times?
2.
2 times. Okay. In this case, it's loss, so it's half. So if I put 100 watts in, how much will I get out?
50.
50 watts. Where does the other 50 watts go? Energy is neither created nor destroyed. Where does it go?
Heat.
Turns into heat. Heats up my cable. If I want to keep my cable from getting covered with ice in the winter, maybe that's okay. Right? Not really what I put it there for, though. So let's take that same frequency of 50 megahertz and go up to RG213. What do I have? 1.4 decibels. So if I were to go through the math, I would find that instead of about 50 watts out, I would get about 80 watts out. That's a significant difference. Now let's take that same cable and go up to 440 megahertz. RG58 at 440 megahertz. What's my loss? How many decibels?
0.9.
Well, it's basically 10. So if I put 100 watts in, how much power do I get out the other end?
100 watts out.
100 watts in,
10.
10 watts. Because 10 times 10 decibels is 10 times. If it's negative, then 10 decibels is 1/10.
Mm.
I have lost 90% of my power. So I then switch that to LMR 400, for instance, and what's my loss per 100 feet?
A lot of cash.
2.7 decibels. Okay, that's less than 3 decibels. which basically means that 100 watts is now going to produce almost 50 watts out, or about 50 watts. Well, that's a significant improvement, isn't it? LMR 400 is a lot heavier and it's a lot more expensive. So there are a couple of ways you can fix that. You can shorten the cable length. Shorten the cable length, shortens because it's per 100 feet, shortens the loss. You could also run more power, but then you'd probably melt your cable. So all this is basically a trade-off, and that's part of why we go through the process of knowing this stuff. Because we have to know what trade-off to make. Okay, moving on. Moving on, we have connectors. Okay, so we're going to put up a line of different connectors. Okay, here we go. We're going to pull up a nice picture of different RF connectors, and what you're going to see is that there are a lot of them. Let me go through and share. Notice there's DINs and BNCs, and there's TNCs, SMA, SMB, RCA. Look at that picture. There's all kinds of different stuff, isn't there? Why do we have so many different cables? Why do we have so many different connectors?
Because there's so many different types of cables that we could connect to.
And so many different applications. Would you want to put an N connector, which is about the size of my thumb, inside a box that has a piece of radio equipment on a circuit board? If I'm trying to make it small, would there be any point to doing that?
No.
I mean, it's the size of my thumb. So, and it's also going to be connecting probably, like you said, to a very small cable, like an RG174. It's lossy, but if the cable's only 6 inches long, who cares? So, all of these different cables have different purposes. Now, the most common one that you're going to see is something called a PL259. So this is a PL259. Everyone see that?
Yeah.
If you've done anything with radio before, you have seen a PL259.
Yep.
This is a standard, it's known as a UHF connector, which is actually universal high frequency. It is actually really bad at UHF frequencies. It's one of those things where they named it before they really understood the implications. So these are typically good up to about 200 megahertz. So you will usually find those on HF equipment as well as lower band VHF equipment. When you go to higher frequencies, you will get to something called an N connector. An N connector, as you see here, looks a little bit heavier duty, and that's because it is. It's got a gasket inside, it's waterproof, and they're a lot more expensive, but they're good up to many gigahertz. There's another type of connector that you will see frequently, especially if you have a Baofeng or any other small handheld radio, which is known as an SMA connector, which looks like that. And SMA connectors are great because, as this says, they operate up to 18 gigahertz, which is really great for a tiny little connector like that. But the problem is, of course, that they're a little bit fragile, and you don't want to bang it around and pull too hard on it or anything like that. And of course, when it comes to cables and connectors, there are two genders because they have to mate together. They are known as typically plug and socket, or more commonly male and female, and you can do the math and figure out why they're called male and female. Okay, let's move on from that. And what could happen? Okay, so we now have to get into something called standing wave ratio. Standing wave ratio is a measure of how well matched something is at an intersection of two different things. For instance, a radio to an antenna, or radio to a cable, or a cable to an antenna. Okay, so Here is standing wave ratio. We're just going to go to Wikipedia for that. I know this is a cheat, but I'm going to do it anyway. Okay, so standing wave ratio. This is an example of standing wave ratio. Notice that you have a standing wave. Right? The fact that it's standing, the reason it's standing is because it is sitting there and is not moving back and forth. The red wave and the blue wave, this is actually a really good graphic. The red wave and the blue wave are traveling back and forth, and as they travel back and forth, they eventually intersect and line up with each other, and they cause that black wave to be created and oscillate up and down. And notice that the black wave is bigger in amplitude than either the blue or the red, right? And that's because our waves are traveling up and down a piece of cable. As they do that, they can basically come into a point where they meet and they create a standing wave inside your cable. That standing wave inside your cable leads to potentially higher voltages than you would ever expect. Notice that the black wave is bigger than the blue and the red. The net effect of that is that, let's say that's a voltage. What can happen is that you end up with a higher voltage than you expect, and if you have a lot of your energy coming back and traveling back on the cable, you can have, let's say, almost double the intended voltage that reaches your transistors. Transistors don't like high voltage, they don't like heat, and what can happen is that can overheat and blow up your transistors. And then you have no power amplifier anymore. So notice we have all this math. We're going to basically ignore all the math. You can calculate it if you feel like it, but we're not going to today. That's left for you guys to do by yourself. So fundamental rule of thumb is that if I have a piece of cable and it's connected to something, this cable is 50 ohms characteristic impedance, and this something has an impedance of 100 ohms. We take the bigger one, whichever one is bigger, divide it by the smaller one. That would be 100 divided by 50, and that gives us 2. That's our standing wave ratio, and it's 2 to 1. Similarly, if I switch this and I make this 25 ohms, that calculation is no longer 100 divided by 50, but it's the bigger one over the smaller one, which is 50 divided by 25, which is still 2 to 1. It's a little bit different. You're going to see a little bit of different reflections and stuff like that, but the net effect is the same. Your standing wave ratio is 2 to 1. So 2 to 1 is acceptable. Ideally, if you have a perfect match, what is your standing wave ratio?
1 to 1.
Yes, if you have 50 ohms and 50 ohms, your standing wave ratio, standing wave ratio is now 1 to 1. I'm just going to erase that and write that. 1 to 1 is a perfect standing wave ratio. You can go through and figure out what your standing wave ratio is based on impedances. The easiest way to think about an impedance mismatch is that if you have 1 to 1 is perfect. 2 to 1 is acceptable, but not great. 4 to 1, you have a problem. Because what ends up happening is that when you hit this mismatch, this is like the easiest way to think about this is, let's say you have a rope and you take the rope and you do this with it and you whip it from one end and you create a wave. You've pulled it nice and tight. You've gone up and down and you've created a whip in the rope, which makes a wave in the rope. And then on the other end, you tie this to a doorknob. What will happen when the wave on the rope hits the doorknob? If your door is slammed really hard and doesn't move, energy has to go somewhere. It'll rattle the door, but if the door is solid, it will get to this point and then it will reflect.
Come right back. Yeah.
It'll come right back. right? How much of the energy got transferred to the door?
None.
Virtually nothing, right? Now, if the door is creaky, it might move the door. That would be energy transfer, right? That's the equivalent of your antenna doing something. So what if this cable is, what if this rope is now connected to another rope? What will happen?
Keeps transferring.
What will
Energy
happen?
keep going.
What will happen if that rope is then connected to another rope
Keeps going.
We'll keep going.
and another rope?
Going.
Keep going.
Continuing to get weaker.
Energy might start fading.
Well, yes, but right. But will you ever see anything come back?
No.
No.
No. Okay. So a perfect match. Let's say I have a 50 ohm a 50 ohm cable connected to my 50 ohm transmitter, connected to a 50 ohm antenna, and it looks like this. Here's my transmitter. It's 50 ohms, and I have connected to a 50 ohm 50 ohm transmission line and a 50 ohm impedance antenna, and I send a signal out here in the form of a wave. This wave will travel up here, and what happens when it gets to the antenna? The impedance is matched, the energy transfers, and how much do I ever see coming back?
Zero.
None.
Nothing, right? It all went somewhere. So here's an interesting analog. What happens if my cable is really lossy? Let's say that we go through that process of picking a cable, and we end up with a cable that dissipates 90% of my energy in heat at a particular frequency.
Scott, Scott, I need to ask you to ask the others who are answering you to speak louder. I hear the question, I can't hear their answer.
Okay. I think you just asked. Thank you. Everybody, you got that?
I did.
Yep.
Okay, speak
Got
nice
it.
and loud. Okay. Okay, so let's say we have 90% of it goes out as heat. That means only 10% goes out up here. Let's say of that 10%, it splits in half and you get 5% out and 5% coming back. Looks like your antenna is doing a pretty good job, doesn't it? I mean, I had 100% going out this way. And of that, and that 5%, I burn off 90% of it. I only have 0.5% coming back because I burned off 90% of that 5% as heat. So if I have 100% of my power going out and only 0.5% going back, that's a pretty good antenna system, isn't it?
Why is any of it coming back?
Because I have, in this case, let's say I replace this with a poorly matched antenna. So let's say this was 25 ohms. So that's a mismatch. All right, so some of the power is coming back. Now I look at my antenna system and I have 100 watts going out and only half a watt coming back. That's pretty good, right? If I were to calculate my standing wave ratio, that is really close to 1-to-1.
Yeah.
Do I have a good antenna?
No.
Do I have a good system?
No.
Not at all, no.
You're losing too much in heat.
Because I lost it. It's so inefficient. I burned off all that energy and heat. So a poor cable, a lossy cable, can mask a really bad problem and make it look like it's okay. So you have to take your measurements with a grain of salt when you do that. So a poorly matched, a poor piece of cable, a lossy cable, can mask a really bad problem. So let's say you have erratic changes in SWR. It could be raining outside. That changes things. You could have a loose antenna, right? You could have a loose connector somewhere. What happens if you're building a station and you find that it's raining outside and your standing wave ratio changes drastically? What do you think might be happening?
You have a leak.
You could have a leak. Yeah. Okay. So let's talk about what coaxial cable is made of. Coaxial cable is made of like a plastic jacket, and then inside it you've got a shield. So here's your plastic jacket, and then inside you have your shield. That's your return line, basically. That's your power going, that's where your power comes back. And then you have a dielectric material, which is an insulator. It's like polyethylene, polystyrene, could be air. Um, it could be like air, it could be like spacers that just spiral around the center conductor. And then you have the center conductor. So, what can you say about the currents that are on the inside and outside? Ideally, you have the same amount of current going in and out. Now, they're not spread as evenly because your surface area of your outside is a lot bigger than the surface area of the inside. But essentially, you've got your current flowing in and out. You have fields operating inside that coaxial cable. So what happens if you get a spot where this cable, like the jacket, gets cut or nicked? What happens to your signal?
Shielding.
This is an open area. What happens to your signal?
Less shielded, water
distorted.
gets in.
It will leak out. Yeah, it's leaky coaxial cable, so that gets lossy. This is actually what's used inside of a lot of tunnels for cellular systems. It's intentionally leaky cable so that people can still have cell coverage from a cable that's run in a tunnel. Okay, so here's another one. Let's say that I have copper in my cable. A lot of them have aluminum. A lot of them have copper. I'm going to draw my cable again. And what is one thing that we require of cable in order to work properly? Cable is made of, the conductors are made of metal.
Metal.
Right? And we have two of them. We have the center conductor and we have the shield going around the outside. Those are made of metal, and on the end of it, we have to put something on here in order to get the signal in and out, right? Whether we solder it or crimp it, there's something that goes on the end so we can actually connect it to the outside world and get our signal in and out. What is one of the biggest enemies of metal?
Rust.
Rust. Excellent. Okay, if we have aluminum or copper and there gets to be water on the inside of it and that gets oxidized, how much current does it now carry?
Or none.
Not very much. Yeah, aluminum oxide is a very poor conductor. We get copper, it turns kind of greenish. It's not very metallic anymore at that point and it doesn't work very well. So, what is the enemy of cable?
Moisture.
Moisture, yes. Okay, so how do we prevent moisture from getting into a cable?
Plastic or
Put it in
rubber.
plastic. We can use lots of electrical tape. We can use self-sealing rubber mastic. I've actually done this where I had a connector that was on a piece of cable on the back of my car. It rode around in the snow and the ice and the dust and everything, and the salt on the East Coast for like 14 years. And when I finally got rid of the car because it died, and I took everything apart, the only part of that entire system that was clean was the cable that was buried inside of what I had put together. Like this right here, that part of the connector and the cable was absolutely pristine. Everything else was basically almost falling apart, but the connector itself was absolutely gorgeous.
Hey,
You
Scott,
had
I got a
rubber
question.
mastic.
Yeah. Question.
So, bringing up that salt and stuff like that, like I live on the ocean.
Mm-hmm.
So,
Good luck.
antennas, yeah, I know.
Good luck.
Antennas, when they get like a rust film on it, is that gonna
No.
Is that gonna screw
No,
up the
the
signal?
aluminum will be fine. Most
Okay,
antennas are going to be aluminum. The copper will be fine. I mean, you're going to want to. Okay, here's the tricky thing about that.
sorry.
No, this actually brings up another very important point. Okay, so we're going to draw a blow up version of a piece of wire. Okay, so here's our cross section of a piece of wire, greatly expanded. And now we're going to turn it so it's on its side. We're going to look at it end on. Okay, so here's our end on view of that piece of wire. The cross sectional area is all of this. DC, as this is being carried by this wire, distributes evenly throughout that piece of wire. So this is DC inside. It fills up the entire space. AC for that same piece of wire looks like this. Where's the current in the middle?
There is none.
There is none. Yeah. AC, basically current follows something called the skin effect. It is proportional to the frequency that is being used. The higher the frequency, the more the current flows toward the outside. And at very high frequencies, it flows completely on the outside. So much so that you can actually replace this piece of solid with what?
Tube?
A tube, yeah. Most HF antennas are actually made of aluminum tubing
Yeah.
because it doesn't matter. So yeah, there'll be a little more resistance when you get to the aluminum oxide on the outside.
hmm
Copper, same thing. If it starts to turn green, it'll still work, just maybe not quite as well. The real problem comes when you're building an antenna. And if you're building an antenna and you have two pieces of aluminum tubing, what happens? Aluminum is very strong. But what happens when aluminum oxidizes?
Turns green.
No, it turns gray.
No. Gray. Sorry.
Aluminum
I was thinking
oxidizes,
the green marker.
and aluminum oxide is not conductive. It's a very good insulator, actually. So when you're putting together aluminum antennas, it is very important inside that joint to use something like deoxit or Adelox or any number of different things which are basically aluminum protectors, and then put them
hmm
together and make sure that that joint stays free of corrosion.
Right. Okay, perfect. Thank you, sir.
Yep. See, that's why questions are so great, because they lead us into other things. Okay. So an antenna analyzer is basically a fake transmitter. Okay, so you remember
Can we,
those?
for 1 second, could we talk 1 more second about that coax thing? So that little
Sure.
cable on the inside, that is what my data goes out, and the big cable on the outside, if I'm talking my modem so I can understand. If that little cable is my data going out, and the wrapping around it, that little cable in the coax is the data from my ISP coming in.
No.
And that is why my download speed is different
No.
than my upload speed.
Nope, they're happening simultaneously.
Oh, then why is my upload speed only like 10 and my download speed's like 400?
Because that's what they give you.
Oh.
Because that's what they decided to give you.
Oh.
So think of like this too. Here's a question. When, let's say you are, see, this is again another really good segue. All right. So let's say that I have my coaxial cable. Anyone still have a cable, at least from somewhere where they get their signal into their TV? I know I do. Right? Not everything is over Wi-Fi. Wi-Fi is a good example of it too. But let's say that we have a cable that is hooked into the back of a TV. This is coaxial cable. Inside that coaxial cable is an isolated world, which hopefully never leaks into the outside world and vice versa, because that'll cause the signal to get lost. But inside that coaxial cable that hooks to your TV, if you pick a channel on your TV to watch, and it happens to be, TV signals are about 6 megahertz wide. It happens to be between 500 and 506 megahertz. Does that mean that there are no other signals coming down that cable at the same time?
Everything's going.
No, there's not. At the same time, there's another one from 506 to 512, and another one from 494 to 50 to 500. Those are all there at the same time. So, because they're all there at the same time, you have selectively chosen which one to listen to, right? Those signals could be coming in one direction. You could also be using the same cable to do, let's say, from 900 to 906, transmitting in the other direction. So this could be like direction in one direction, those are your TV signals, and this one could be something else. It is you can have a transmitter and receivers working on the same cable and antenna at the exact same time. So it is important to now bring something up, which is the fact that there is this frequency spectrum that we are going to work in. It starts at 0 megahertz and goes up to infinity megahertz, just like on that frequency chart, right? Just because there is something here, let's say that this is at 500 megahertz. Does that mean there can't be something on that same cable that is at 650 megahertz? And something else on that same cable that is at 1125 megahertz.
It's all there.
It's all there. If you were to look at this in time, like a time graph, you would see that you have this frequency, and you would also see another frequency, which is a higher frequency, and then you would have another frequency, which is a slightly higher frequency. Those are all there. So this is the time graph. And those, you don't see a distinction. What you see, if you're looking at those, is the added mixture of all of them. They all add together. So what you might see actually might look like this. And all those different frequencies are contained in the spectrum. They all make one big mess looking thing. The conversion from, we call this the time domain, and we call this one down here the frequency domain. They are interchangeable with each other, but you have to basically unwrap the sine waves to figure out what's there. There was a scientist and more of a mathematician. You might have heard this name before. Anyone ever heard its name before?
Yes.
Oh,
Yeah.
yes.
Fast Fourier transform.
Jean-Baptiste Francois Fourier, right? He figured out and was the first to implement something called a Fourier transform, which takes the time domain and basically convolves it with a whole bunch of different functions of different frequencies and was able to generate a frequency domain representation of what we see. That is the same thing that is used in every digital signal processing circuit that you see. There's a digital Fourier transform. There's a shortcut, which is known as a fast Fourier transform. This is what allows us to do most of the heavy-duty frequency-based math that we do today with electronics. So it's important because I'm going to probably seamlessly work between the time domain and the frequency domain as we continue through this. But I'll try to make sure that I mention the fact that okay, we're going in the frequency domain. I'm going to draw a frequency chart. Just to know that if I tried to represent this in this, it would be a hideous mess. And that's why Fourier transforms are so useful. We use them every day. Okay.
I have a question about this chart.
Uh-huh.
So we've got all these different wavelengths going through the wire.
Yeah, we
and
do.
let's pretend that the energy is 100. Does each one have 100 then, or do they share that energy?
Depends.
And then with the
It totally depends.
faster. Oh,
If you have a broadband amplifier that's a 100-watt amplifier, you could be transmitting all of them with a total of 100 watts. You could have 40 watts in one signal and 11 watts in another, and
okay. So it depends on what I want when I set it up. If I set it up correctly, I can get it the way I want it.
yep,
Okay.
you're the boss. All right. Okay, so now one thing that we mentioned before yesterday was a dummy load. A dummy load is a non-inductive wire wound resistor, and we use that as a phony transmitting antenna, a perfect antenna. Okay, so whoops, I shared the wrong thing, wouldn't you know? Okay, I'm supposed to share this. Okay, so now notice we're into amateur radio signals. Okay, so that was our segue into frequency domain. Because when we start modulating things, we deal with amplitude and frequency modulation. Okay, so we are now on page 57. We got a ways to go, but we're going to be okay. We're on page 57. Okay, yes, okay, here we go. What we're going to draw is a sine wave of constant frequency. As drawn, this is constant amplitude. I can take this is known as a carrier. It's a very high frequency with respect to some other frequency that we're dealing with. So let's say this is at 21 megahertz. That's our carrier frequency. We have another frequency which is much, 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 much less than that, which is your voice, which looks like that. We can multiply these two signals together, and we can modify it so that our modulated wave looks like this. Essentially mimicking the envelope of your voice as drawn above. We're changing the amplitude. This is known as, everyone?
Amplitude modulation.
Amplitude modulation. This is known as AM, and this is in the time domain. If we now look at the frequency domain, we would see that we have our carrier frequency right here, and that the sidebands which contain the information about your voice would spread out left and right. 0 is way over here. Infinity is way over here. So the blue is the frequency domain. So what we would see is what do you think we would call the area to the right, which is above the carrier frequency?
Upper sideband.
That would be, because it's plus, it's on the positive side, higher frequency. We would call that the upper sideband, and on the bottom we would call that the lower sideband because it's on the negative side. Okay. So what we can do with this is now we can, if we choose, we say, okay, well, the upper and lower are just reflections of each other. Well, if we have 100 watts of energy 100 watts of power to put into something, why would we waste it sending two copies of the same thing? I could, when I'm building a transmitter, I could take this and I could say, oh, we're just going to get rid of the lower sideband and only transmit the upper sideband. I've just doubled my power, essentially. I've doubled the effectiveness of my signal. And the other thing is the carrier can contain a ton of power, and all it is a marker frequency. So what we can do with that is we can decide we're not going to transmit that either, so long as on the other side it gets put back into the signal in the receiver. So when we get to the other side, we will be able to re-inject a carrier frequency and be able to decode the information that's in the sideband, which is your voice. So one of the interesting things that happens is that when we are doing that, we can actually tune our receiver. And if I get lucky, I will find somebody on single sideband. I can share their signal, and we will hear what happens. This is why WebSCR is so great to have. And let's pick one. What time is it in Europe? Let's see. It's evening. I hope we can find someone. Somebody talking. Oh, I think we found someone. Okay, I'm going to share this, and we will understand what it means to. Can everybody hear that? What it means to.
Yeah.
Okay, what does it sound like?
Someone's doing Morse code.
No, that's a voice.
Oh, wow.
What's wrong with it?
Sounds robotic.
We're on the wrong. We shifted the frequency. We injected the carrier frequency in the wrong place. Notice this is what it really sounds like.
Much better.
Notice what happens if I inject the wrong carrier frequency.
Slows it way down.
I can't. No, I can't. It
Like
changes.
it's not tuned
It
in
changes
right.
the pitches, and you can't understand it.
Doesn't sound tuned in.
Right. I'm not tuned in properly, essentially.
Hey Scott, you're showing the wiki and not. I don't know if you're
Oh,
trying to
whoops.
broadcast
Yeah, that should have replaced it. Hold on. There we go. Make sure I got the right thing up. There we go. Stop it! Can y'all see it?
Yes.
Okay,
Yeah.
so now what we're looking at is this person's. Okay, so we could hear that okay. Unfortunately, we can't find somebody. Oh, there's another one. Notice what happens if we tune it wrong.
Distorts it.
It distorts it because we're basically saying that we're putting the carrier frequency in the wrong place. We're moving that sideband. This is upper sideband. We're moving this into the wrong spot. You know something's there, but you can't figure it out. Same thing is if I pick lower sideband and I try to tune it in. Then the highs are the lows, and the lows are the highs, and you can't understand it at all. So we're basically using the receiver to help us rebuild the signal. And if we tune it wrong, it doesn't work. If I try to listen to this using amplitude modulation, notice what you hear. And why doesn't that work? What's missing?
Sounds like the lady on Peanuts.
Yeah, what's missing? There's a certain piece of that signal that we drew that is missing.
The carrier?
The carrier is missing. AM assumes that the carrier is already there, so it doesn't work. Okay, so that is called amplitude modulation. Now we're going to do another one, and for this, okay, we are going to um, move into the different domain. So we're going to pick blue just because. So we're going to be working in the frequency domain, and we're going to pick a frequency. And here's our frequency of our carrier, and here's our modulating signal, which is your voice. It looks like that. And what we're going to do is now take this modulating signal, which is your voice, and we're going to modulate. Modulate means to change this frequency. And what we're going to end up with is that we're going to move it up and down. And the amplitude is basically not going to change. We're going to create motion of that motion of that frequency up and down in time. And sometimes there'll be more than one. Sometimes there'll be a whole bunch of them. So what we end up seeing with frequency modulation is we end up seeing a whole block of frequencies that are filled in. So
is this like your volume button? Which button would this be? This is this volume or is this power? I'm sorry.
This is neither. This is, okay. I mean, we're modulating using our voice. Essentially, the strength of the signal and the frequency components in your voice cause these sidebands to be created. They cause a change in the frequency. If this is, for instance, if that center frequency is 144.529 megahertz, then you will contain frequencies that are above and below, and they are all very important because those different frequencies that are generated contain the information that is your voice. On the other side of things, when it finally gets to the other end, you basically have to unwrap exactly what you did to reclaim your voice and figure out when it went up and down, how fast was it going up and down, what amplitude was going up and down, and figure out what your voice was. So one advantage of AM is that AM is a very good weak signal mode. Single sideband is a very good weak signal mode. If there are two signals at the same time, you can actually hear them both. FM, on the other hand, this is FM, and we'll also use PM, which is phase modulation. That's sometimes used for generating FM. What happens is if I have another signal right here, which is too close, doing the same thing, what do you see happening right there?
Overlap.
They overlap, and they distort each other. And unfortunately, unlike AM, when that happens, what you end up with is something called doubling, and FM has a nasty habit of, if there are two signals that are like on top of each other, nobody wins, and they obliterate each other. This is largely why aircraft do not use FM for air traffic control communications, because if you hear a double on AM, you can still at least make somebody out. If it happens on FM, you lose everything. So that's why air traffic control is still, for the most part, AM. Okay, so that's FM. FM, the amount of spread that you get on either side is known as the deviation of the signal. The receiver, we're going to eliminate this red signal right here because it's just in the way.
Before you go on, can I ask a question?
Sure.
Did I hear you say that those sidebands are mirrors of each other?
Yeah, on AM, yeah. That's why we do single sideband, because we save some of the energy and save some of the bandwidth, and we're able to reuse it for more signals. Yeah, upper and lower sideband are redundant.
Scott, I have a question.
Yep.
I've noticed that most of the time I see people, if they're going to operate on sideband, they seem to always select the upper sideband. Is there a particular advantage to that, or is that just how things develop? Is that just
the break point is 10 megahertz. Anything above 10 megahertz, you use upper sideband. Anything below that, you use lower sideband. And that actually comes from design of the equipment back in the 1950s. It was
okay?
easier.
Is that because the upper sideband or lower sideband at those frequencies yields a particular advantage, or is
Nope.
that just the way things develop?
The advantage is inside the receiver. It was easier to when doing super heterodyning.
Yes.
It was easier to make lower sideband on lower frequencies because of the choice of frequencies of choice of mixer frequencies.
Okay.
And
all right. Thank you.
Above 10 megahertz, it was easier to use upper sideband.
Okay. Thank you.
Mm-hmm. Okay, so what we've done now is we have this thing called deviation. Typically on an FM transceiver, like a handheld radio, your deviation is going to be plus or minus 5 kilohertz. So a receiver will be listening at typically plus or minus 5 kilohertz. So if you are over deviating, remembering that the deviation is what actually contains your voice, and your signal ends up being this wide, and the receiver is only listening in the red zone that we've drawn, what happens to the rest of your signal?
It gets cut off.
It gets cut off. If it gets cut off, it gets distorted. So if you're over deviating, the person on the other end won't be able to understand you. Over deviation is caused by too much amplitude. How do you make too much amplitude into a microphone?
Overmodulating?
You yell. You're yelling into the microphone. If you're yelling into the microphone, you'll over deviate, and then people won't be able to understand you. So speaking louder is not always the solution. It's sometimes the solution. Okay. So it's time to start looking at bandwidth. Okay, so we're going to look at the frequency domain again. I really should have drawn this in blue. I ended up standardizing on blue. All right, so frequency domain, 0 megahertz up to infinity. Okay, so we're going to pick a particular frequency, and we're going to make, let's say, we're going to pick 10 megahertz. So what we have is upper sideband, lower sideband. So this is AM. AM takes up 6 kilohertz of space. Single sideband would take up half of that. What would half of that be?
3.
Is 3 kilohertz, right? Okay, so now we have some other modes like Morse code. Morse code is basically just on and off, and Morse code fills up about 150 hertz. We have other modes such as PSK31 and FT8 and things like that are even narrower than that. So we can draw this one, for instance. We'll go PSK31. That's a digital keyboard to keyboard mode, which uses PSK, which is phase shift keying. It takes a signal and it basically just shifts the phase a certain amount. That could be 180 degrees, it could be 90 degrees, it could be 45 degrees, depending on how you're doing it. PSK31 takes up a bandwidth of 31 hertz. So, if we are trying to send a signal through the ether to the other end, which of these is going to be the most efficient given a certain amount of power?
Phase shift.
Yeah, PSK31, because all your power is going in this tiny little 31 hertz space. I mean, that's basically a physical space on the spectrum. FM is this big, is 15 kilohertz. We can also do this thing called television. Fast scan TV. we're allowed to use NTSC television, which is 6 megahertz in bandwidth. Okay, so where would we do television? What would happen if we had a 6 megahertz wide signal? It would go down all the way to 7 megahertz and all the way up to 13. Is that going to work?
Not efficiently.
and there's a lot of other people in there, right? That's a 6 megahertz wide signal. Well, okay, so now we're going to look back at the band plan and understand where that is actually usable, because it is usable. And in fact, you will see that in the band plan, this thing called amateur television is used. And notice it says amateur TV fast scan. It's in the blue sections. It takes a lot of room. The lowest bands that we're allowed to use it on are 70 centimeters, which are in the UHF range. And then up here where we get into the microwaves. And why is that? How wide is, let's say, 23 centimeters? It goes from 1240 all the way up to 1300. How wide is that?
$60 megahertz worth?
That's 60 megahertz. That actually contains our 6 megahertz TV signal very, very well. It allows us to make use of it. So that being said, certain modes work really well for certain places. FM is good on VHF because there's room. Not so good on HF because it takes up 15 kilohertz. Let's take a look at this frequency band again, and we're going to go down to the 40 meter band. How many kilohertz wide is this? It goes from 7 megahertz to 7.3 megahertz. That's 300 kilohertz wide. How many 15 kilohertz wide FM channels, FM stations could be on there at the same time?
20?
20. That's it. On any given day, there are hundreds and hundreds and hundreds of narrow band signals on that band. So the lower the frequency you go, the less space you have. Now, at that same time, you'll remember that we brought up this god-awful frequency chart yesterday, which I'm now going to share if I can figure out how. I'm going to try. I don't know why it seems to be flickering. Okay. Is that being shared? Can everybody see that frequency allocation chart?
No. Yes.
No.
Yes.
Yes? Yes. Okay. All right. So,
Scott?
Yes.
Did you say the lower the frequency, the less space you have?
Let's take a look. So, we're going to look at the high frequency spectrum. What's the frequency range for high frequency, everybody? Do you remember this? Because this is on the test.
300 to 3,000.
3 to 30 megahertz.
3 to.
So there's 3, and there's 300. Or sorry, there's 30. What is the total amount of space between 3 and 30?
27.
27 megahertz. Okay. Look at VHF. You have between 30 and 300. What's the total amount of space there?
270.
270. If we look at UHF, we have between 300 and 3000, which is 3 gigahertz. How much space do we have up there?
2.7 gigahertz.
Yeah, 2700 megahertz. Okay, so let's say we have a mode such as Wi-Fi, which we want a certain amount of bandwidth in order to carry our signals, because that's, we don't want slow Wi-Fi. We want fast Wi-Fi, right? Nobody wants slow Wi-Fi. You want at least, let's say, 100 megahertz of bandwidth. You're certainly not going to find that on HF. You're not going to find it easily on VHF. Well, on UHF, between 300 and 3000, you may find it there. And in fact, if you look on this chart, you will see that at 1.2 gigahertz, which is going to be up here. We will find right here next to this amateur band, we will find this radio location and satellite and stuff like that. There's a 1.2 gigahertz ISM band. There's another one at 9 and 15. But then the big one that we'll find is right up here at what's known as 2.4 gigahertz. 2.4 gigahertz, that is what we think of as Wi-Fi. So people want more space. They want 5 gigahertz cellular, right? Because it has more bandwidth. Well, that's way up here. Notice we've got a ham band here. We've also got satellite. We've got fixed stuff. But in there somewhere is 5.8 gigahertz Wi-Fi and 5.8 gigahertz cellular. And the reason we put that there is because there is just that much more room to have big bandwidth stuff. That makes those high bandwidth applications and high bandwidth frequencies match very well with places that there is available bandwidth. That's why those frequency ranges are so heavily coveted, because, well, if you're putting up let's say a cellular system, why would you want to limit the amount of coverage? Why would you want to give people slow cellular service, right? You want to give people lots of data, big wide spaces to download all their movies and stream and stuff like that, and do live streaming. You can't do live streaming if you don't have bandwidth. So those frequencies are heavily coveted. And the other thing, of course, is that I want to point out that us amateur radio operators up here, we've got frequency bands that are into the gigahertz. This is into the gigahertz. We've got other frequency bands. If we look at the NTIA chart, as Kent pointed out yesterday, anywhere you see teal is a ham band. So, oh look, here's one at 76 gigahertz. The antennas are really tiny. Here's another one at 10 gigahertz. Here's another one at 5.8. Here's another one at 3.3 gigahertz. Who do you think wants these? Who do you think is willing to pay through the nose for those bands?
AT&T.
AT&T and any other satellite company and anybody else who wants to use them. So we are under what we would call constant attack for our frequencies. Because what are we using them for? We're using them for personal experimentation and setting up our own networks. Do we make any money on them? No.
No.
Does AT&T make any money on them? Well, they sure would if they had them. So they are constantly under attack by commercial interests to try to get them from us. So it is really a case of us and them. And we have an organization which is called the American Radio Relay League, which I mentioned at the beginning, and that is essentially a representative organization for ham radio in the United States. And so a part of what they do is lobby on Capitol Hill to say, you know what, we're using those frequencies for this and this and this and this, and we provided 200,000 hours of volunteer effort to serve the public in the last year at a cost of about $100 an hour. Well, that's $20 million worth of service, which if you take those frequency bands away, you will lose that public service worth $20 million. Do you really want to sell it to AT&T? So that's what they're on Capitol Hill doing.
I have a question. Back in the day where I lived out on a remote place, I could only use dial-up. How does this coincide, or does it at all?
I don't think it does.
Okay.
Dial-up
was
is
slow.
Yeah, well, dial-up is over wire.
Yep.
I mean, modulation is modulation, but you could only have so much bandwidth on a pair of wires.
Mm-hmm.
Everybody ready for a 5-minute break? I know
Yes.
I am. All right, see y'all in 5 minutes. Think about questions.
When you pour the vinegar down or the ammonia down, what ammonia? The vinegar, do you put water with it or just vinegar straight?
Straight fast. Really, really dry.
When it's dry,
Yes.
Hey, MS Heidler, you're broadcasting.
if you spit in the shower,
Over.
blow your nose.
No.
Thank you. Ohio State, I think they play OSU. Maybe it's Iowa. They're going to get their butts whipped today.
Just a reminder that you might not be muted and you think you are, so we can all hear your conversations.
That's you, M. Scheidler.
Okay, so before we start back up, time to ask questions. If you're back.
I have a question. Why, or I was kind of looking it up, but why is it more coaxial based rather than fiber?
Well, I mean, part of it is that fiber is great for carrying not a lot of power. I mean, fiber is fabulous at carrying small signals, but fiber is not going to carry 100 watts of RF.
That would make sense, I guess, due to it
However,
being great.
however, however, let's say you have a radio that has an RF deck, which is your RF amplifier, and your control circuitry, and they're separate.
Okay.
It is entirely possible to have a fiber optic connection between there, but there's no real reason to. I mean, you could just use shielded twisted pair. I mean,
Right.
you're not moving that much data.
Okay. That would make sense. Yeah. It'd be more expensive that way too if
Yeah,
you use it. So
yeah, fiber's not cheap.
beneficial. Yeah. All right. Thank you.
Scott, this is
Mhm.
Lillian. Early in the session this morning, you were asking us to note the difference between resistance and impedance.
Yes.
And I couldn't write fast enough.
They're
Resistance
similar
is
but
the
different.
ability to block what?
Well, resistance is DC, exclusively DC. All right. So now, if I were to draw that graph again, I have the resistance axis and this thing called the reactance axis. So there's resistance.
Yep.
And in fact, reactance is plus and minus. There's no such thing that we actually work with typically that's negative resistance. So resistance is always positive, 10 ohms, 20 ohms. But reactance, this is inductive up here, and this is capacitive. Those are reactances. And again, they're perpendicular to the resistance axis. So resistance is exclusively in the realm of DC. Reactance is how something behaves with respect to AC. Impedance is the net effect of the two.
Thank you.
So we consider impedance to be how something reacts to AC current, because it kind of takes into effect the DC portion also. All right, everybody ready to start again?
Yep.
Yay! Today is actually the easier day, believe it or not. It's the shorter day and it's the easier day. So you guys have, when I said congratulations in that note I wrote last night, I said congratulations survivors. You made it through the first day. That's the bulk of the effort. So, all right. So today we're going to talk about, in addition to analog stuff like Morse code and single sideband, we're going to talk about packet and PSK31 and other digital modes. Okay, digital. What's the difference between analog and digital, everybody?
Ones and zeros.
Ones and zeros, yeah. All right. So, can you take a voice is analog, and convert it into something digital?
Absolutely.
Absolutely. Where do we do that?
Everywhere.
Such as?
Modern day radio is a lot of it.
We're doing it right now.
Yeah, we're doing it right now.
We're doing it right now. Basically, the only point at which there is an analog signal is going between my microphone and my computer. Everything else is a digitized voice of me, digitized version of my voice. And the same thing with everyone else. Same thing with all the pictures, right? A picture that you're looking at on the screen is an analog thing, right? You're not just a bunch of ones and zeros when you look at the screen. But when it's being transmitted, it's all in the form of ones and zeros. It's all digital. What are some advantages of digital versus analog?
Space.
Yeah,
the amount of space it takes up.
You can compress it. What else? There's a really big one. What was that, Charity?
It's more clear.
Oh, why?
Oh, yeah.
Error correction.
I heard error correction. Who said error correction?
Sarah, I did.
Sarah, yay, Sarah. Okay, error correction. So, what I'm going to do is, let's see. I'm going to draw something right here, and okay, whiteboard. All right, and I'm gonna unshare this. I'll share that in a minute. Come on, behave. There we go. Okay, so if I have a signal that looks like this is my voice, and I sample it and I said this is a level of 16, this is a level of 14, this is negative 11, this is negative 6, and this is 15, and okay, if I transmit this signal and it gets distorted just by itself, and there's like static or something like that, and you receive it like this. Does that sound like me anymore?
No.
That's not my voice anymore, is it? Okay, so we're going to take that signal and instead we're going to make it and say we're going to sample it every so many milliseconds, and we're going to take a bunch of samples and levels and we're going to record them, and we're going to take those values and make it into a string of ones and zeros. So 1 and then we take that and we make a signal that looks like this. For every 1 we transmit one of these, and for every 0 we transmit one of these. And there's noise that happens. So we have this string of things that looks like this. But now we add some noise, and it looks like this. Can we still kind of figure out what it looks like? Knowing that it's either one of two things. It's either a 1 or a 0. Those are our only options. Those are the only things it can be. Right here, what would our guess be?
Yeah, 0.
That'd be a 0. Even though it looks hideous, that'd be a 0. That would be a 1, and that would be a 1, and that would be a 0. And that's basically what we sent. No matter how distorted it got, it actually looks okay, kinda. Right? Because there's only two possible choices. Up here, looking at the analog signal, it could be anything. You add the noise to it, and your signal's totally distorted. So, digital is very, very resilient when it comes to noise. The other thing we can do with digital is we can say, okay, I'm going to send 5 bits. Somebody give me a combination of 5 ones and zeros. Any way you want it.
1 0 1 1 0.
1 0 1 1 0. How many ones are there?
3.
Okay, is that an even or an odd number?
Odd.
We're doing something called parity. Okay, odd. That means I'm going to add another 1. Now, I have an even number. Okay, so now let's say that this goes through a signal channel, goes to the other end, and somebody gets this. 1 0 0 1 0 1. Something got flipped. This bit got flipped by noise. When the decision was made on the other end, it was decided that that's what was heard. Is that a valid thing? Because this always ends up being an even number. We have made it so that we have an even number of ones. How many are there right here? There's 3. That's odd. We know that something got distorted, and we can say that's not valid, we need it again. This is known as parity. And this is error detection. Now, you can add more bits and say, I'm going to add 3 copies of the same thing. For instance, I added a 1, I'm going to add 2 more 1s. And then I might get something that on the other end gives me even a little bit more ability to figure out not just that there was an error, but which error it was. Where the actual error was, if I'm really creative about it. And that's called error correction. So, digital communications allows us to do those kinds of things, which makes it extremely resilient, which is why when we're dealing with sending information back and forth over the internet, we use digital communications. That's why we use digital communications for voice over the phone. That's why we use it for TV. Because it's digital, we can do this thing called compression. and we can compress those signals and make it take up less space, which means we can send it faster. So all kinds of cool stuff you can do with digital. Okay, so one of the things you can do with digital is known as packet. Packet has existed for a very, very long time. It was actually the basis of information traffic over the internet. If you've ever heard of something called AX.25, AX.25 is how information is often shared over the internet. Yeah, we do have 20 people less than yesterday. That's pretty normal, actually. I can go into those statistics after. So AX.25 packet is a method of sharing data over the radio. Essentially, it uses FM and it modulates the FM signal with a digital voice, with a digital stream. All of these, we are now looking at Portland, I believe. Yep, there's the greater Portland area. There is an application of packet radio, which is again FM radio with digital communications, where you basically combine data being sent with various different kinds of information like location data, weather, the velocity, altitude, things like that. And you can then combine that with a map and put it on a map. So this is APRS, which is the Automated Packet Reporting System. And all of these locations that you see here, every weather station, like occasionally you'll see a car, those are packet stations that there's a car and I can click on it and see where they're going. Oh look, 11 miles an hour, 456 feet altitude. So essentially what you've got is graphical information or geographic information systems combined with radio. You can use this for real-time tracking of things, such as a weather balloon or such as a high-altitude balloon. There are a lot of people who put together like an 18-inch party balloon or 36-inch party balloon with a 12-gram payload on it, which is a complete packet radio transmitter with transducers. And it gets up to about 35,000 feet and floats around, and if you're lucky, it catches a nice wind and goes across the ocean. And everywhere it goes, if it's got a little solar panel, it transmits its position and people around the world can see it and put it on this map. And that's known as APRS.FI if you want to take a look. And here's APRS.FI. Okay, other cool things that you can do with digital communications. You can set it up so that when you're transmitting data back and forth, there's something called ARQ, which is automatic repeat request. That is something that is built into Packet as well as lots of other digital modes, which basically says that if you have a lost packet, you have information that isn't valid, it can send a request back that says, I lost it and give it to me again. It slows you down a little bit, but that's okay. Because it's better to have correct information slow than bad information fast. Again, PSK is phase shift keying. That's basically you get a signal that looks, let's see if I can override that. Can everybody see the whiteboard?
Yeah.
Okay, so here's a carrier wave. It gets to a certain point and it says, up, I'm going to shift it by 180 degrees. I was going down and now I'm going up. That causes a discontinuity. Here's another one. Wherever you see those, that is an indication that something happened, like a value of a 1. It takes up very little bandwidth and it can be used for binary, which is either 0 degrees or 180 degrees. You can also set up, so that's BPSK. You can also do QPSK, which is quadrature phase shift keying, which is 0, 90, 180, and 270. And then there's something called 8PSK, which is exactly what you'd think, 1, 2, 3, 4, 5, 6, 7, 8. You have 8 different phase shifts. If you have 8 different phase shifts, you have 8 things. That means you can encode 3 bits at a time. So, and you're only basically limited by the channel capacity and how solid the channel is. So lots of ability to do that kind of thing. DMR is digital mobile radio. Most people still use analog FM. DMR is basically taking your voice inside the radio, converting it into a digital bit stream, and sending those digital signals across essentially a half of a voice channel. The voice channel is split in time into 2 different channels. One group gets it for a period of time. The other group gets it for a period of time. It's called time domain multiplexing. And essentially what it means is that if everybody is synchronized on the same time sequence, then everybody knows that if I'm on this group, I'm on part A, and if I'm on this group, I'm on part B. And they don't hear each other. And because digital voice takes up less bandwidth than analog voice, you can stuff 2 signals into 1 channel. All right, WSJTX. This is something that was devised by a guy named Joe Taylor, who's a Nobel laureate, who also is really his focus in his academic studies is radio astronomy. So of course he would focus on Earth, Moon, Earth, which is moon bounce, and meteor scatter, as well as weak signal propagation. That's his thing. So he took his professional life and his ham radio life and merged them together and created this thing called WSJTX, which runs a mode, one of them, called FT8, which is a very, very good weak signal propagation mode. It was originally designed for something called moon bounce. And so, anyone guess what moon bounce is?
Using the moon as a repeater?
Using the moon as a repeater, as a reflector, basically. So you have a satellite dish up here, or a bunch of Yagis, and you put, let's say, 1.5 kilowatts of power up into your dish, and you aim it at the moon, and when it gets there, it bounces off in all directions, and some of it will come down, hopefully, over here, where there's another person with a dish, and okay, you ready for this? The typical path loss is 230 dB. What does 230 decibels mean?
That's a lot of loss.
Every 10 decibels is how many times?
10 times.
10 times. So if I lost 230 dB, that is 10 to the minus 23rd power of my original signal. And that is why he came up with this mechanism, which is an encoding scheme which works very well at weak signals. Because if you put out, let's say, 1,000 watts and you have effectively a gain of 1,000 times, you have 1 million watts heading up equivalently. But you then multiply that by 10 to the minus 23rd. So you have 10 to the minus 17th watts being received on the other end. How much power is that?
In the chat.
Come on, it's nothing. It's like nothing. Yeah. So let's say you have another 30 dB of gain here. And so now it's down to 10 to the minus 14th. This is still in the picowatts. It's in the fractional picowatts. There's virtually nothing there. So he basically came up with an incredibly redundant and very, very slow but very resilient system for sending data. It's extremely difficult, but it's not as hard as it used to be. So that's FT8. Okay, so here we go. We are into safety. Okay. It is very easy to kill yourself using radio and electronics, right? The easiest way to kill yourself is by getting an electric shock. You get an electric shock, remembering that people are basically made of salt water. Salt water is a conductor. It takes 100 milliamps to stop your heart really well. That's not a lot of current, is it? You have skin resistance. However, if, let's say, you get a cut and you get something sticking into your finger and it gets into the salt water, it finds a way through very, very easily. Your body is extremely conductive. So you can heat up tissue and cause a burn. You can disrupt the function of cells, and you can cause muscle contractions. And the muscle contractions are what stops your heart. Three-wire system. In the United States, at least, we have 3 wires. Green is always ground, the black is the hot wire, and the white is the neutral. That's just memorization. To protect yourself against shock, you want to ground your station using the green wire. The green wire is very important. You also want to install mechanical interlocks because some transmitters might operate at 3,000 volts. You stick your finger inside a 3,000 volt box, you might hit something, it might arc to you, in which case you will get a nasty shock. I've gotten hit with 250 volts DC. I was a kid. It was very unpleasant. Purpose of a fuse is to remove power in case of overload. Always put a fuse or circuit breaker in line with the 120 volt circuit. Put it in the hot wire. You should never use the wrong fuse because somebody designed it that way. They designed it for a particular value. If you shut off a power supply, oh look, you could still have a charged up capacitor. Like I was saying about the old TV. TV can carry a lot of voltage on it. 12 volt storage battery. In your car, you typically have a lead acid battery. Well, it's got lead, which is toxic, and it's got sulfuric acid, which is a strong acid. So if you take a lead acid battery and you overcharge it or you discharge it really, really fast, you get hydrolysis, which breaks apart the water that's in there, and you get oxygen and you get hydrogen. The really bad part is that you get hydrogen, because what can hydrogen do if there's a spark?
Explode.
Think Hindenburg. Yeah. And so you now have a small explosion because, you're trying to recharge a battery and you touch something to something and it makes a spark because it's electrical. You now have an electric spark and hydrogen gas and sulfuric acid. So what you've done is you've basically showered yourself with sulfuric acid. So that's why you never use the battery negative terminal. You always, if you're going to connect to ground, you find the ground for recharging a battery somewhere else on the chassis frame where there's no hydrogen gas accumulated. Antenna and tower safety. When putting up a tower, we every year lose at least one, and very often very well-known ham, because they're doing some work outside and they forget that there is a power line nearby. Just last year, there was somebody taking down an antenna off a tower in Texas. Extremely experienced and well-known ham. He was part of the ground crew, and he saw the antenna getting hung up on one of the guy wires for the tower, and he reached up to grab the antenna. What he didn't realize was that the other end of the antenna was touching a 12,000 volt power line. And it didn't have a path to ground until he touched it. And he was killed instantly. So you want to maintain at least 10 feet between every antenna that you're working on and the power lines. That gives you a nice safety margin. And a utility pole, don't use a utility pole unless it's, your power pole. Even so, if you do that, there's high voltage on the pole. It's probably going to, if there's a transformer, it might make some RF noise, in which case it wouldn't be very good anyway. And those power lines out there carry 12,000, 13,000 volts just in your neighborhood. If you look up on the street, they're extremely high voltage.
No power lines.
Hmm?
No power lines here where I live.
Yeah, well, they're somewhere. I mean, they're underground.
They're underground.
Yeah, if they exist at all. I'm fortunate. I don't have overhead power lines in my neighborhood, but a lot of people do. What hazard is caused by touching an antenna that's transmitting? And because you get very high voltages and it's at a very high frequency typically, you can actually get an RF burn, which looks like a little pinhole in your finger. It really hurts too. Causes a little black mark. You can even get it from a handheld radio. I've had that happen. If anybody wants to know why, I can go into that too. You want to know why? Okay. Okay.
I do.
Yes. Okay.
Yeah.
Here we go. All right. So here's your handheld radio. Here's the antenna on it. How long is that antenna usually in wavelengths? If it's a vertical.
3 inches.
Yeah. Okay. Well, typically it's going to be a quarter wave vertical. Sometimes you'll have a loading coil in there that shortens it. A full size quarter wave vertical can be a little bit long. So sometimes you'll put a loading coil in there, which will shorten it up. It'll kill your efficiency, but that's okay. So, okay, what does a quarter wave vertical need? Does everybody remember we drew one yesterday? What's missing?
The ground plane?
The ground plane. Okay, so when you are using a quarter wave vertical, if you have your radio sitting here, what is functioning as the ground plane?
The table.
Well, if it's a plastic table. The radio typically has a metallic chassis. It's not going to be the right size though, right? So if you have a plastic table, it's not going to be a very good ground plane. If you have a metal table, it is going to be a better ground plane. How is the radio, because it's typically going to be painted, connected to the metal table?
Capacitively coupled?
Capacitively coupled. Yeah, it basically looks like a capacitor. It will cause a current to flow and basically mimic the other half of the antenna. But what if you're not lucky enough to have it on a metal table and you're just walking around with it?
You become the ground plane.
You become the ground plane. That's right. So you're holding the radio in your hand like this. Well, you do a Simpsons hand, only 4 fingers. All right. So you are the other half of the ground. You are the ground plane. So here's your body. There's your head. All right. So you're the ground plane. So now here's a question for you. How are you coupled to the radio?
Passively.
Because you have the radio chassis, which looks like this, and then you have your skin, and then you have a bag of salt water. So you're capacitively coupled to the radio. You are actually carrying current, which is at the same frequency of the transmitter, which is basically mimicking the other half of the radio. So now here's a question for you. What happens if your skin, for instance, is damp and sweaty? It actually works better, right? It's almost a solid connection, right? It gets better. Well, what I found is that I had a radio that had a little screw on the back, which I wasn't using, and I was sweaty at the time. And when I moved my hand around, the sweat actually acted as a nice little point for high current to flow directly, but then it broke when I pulled away a little bit, and then when I went closer, it made it again. And there was at 5 watts with my handheld enough power to give me a nice little RF pinhole burn right there on my hand. Looks like a little black dot and really hurts. So RF hurts. RF can actually cause some pain. So
Does the black dot go away?
oh yeah, it heals. It heals, but it hurts. Without a doubt. Okay, let's see. What do you do when climbing an antenna tower? You wear a belt. You never climb by yourself. And you make sure that you, for instance, if you're going to have somebody down at the bottom of the tower, making sure that you don't get stung by a bee and die on the tower or have a heart attack and you have nobody there to help you. How do you make sure that your helper doesn't get killed if you're using tools up there? What do you make
Lanyards.
what do you make your
Leashes
helper
for all
wear?
your tools.
Yeah, leashes, or what do you make
Hard
your
hat.
and what do you make your
Hard
helper
hat.
wear? Hard hats, yes, hard hats, safety glasses. All we in industry we call it personal protective equipment. So always lots of PPE. Okay, when using a crank up tower, I just saw a picture of this. Somebody had a crank up tower fail. Essentially, this is a system where you have a crank and a big wire rope that pulls the tower up from inside. If you're going to be climbing it, it has to be retracted, or you have to have locking devices installed. There was just a picture on one of my Facebook groups of somebody's tower that the metal rope broke internally, and it was a 75-foot tower holding some big antennas, and it collapsed to about a 30-foot tower in a very, very, very short time. Destroyed the tower, destroyed all the antennas. So very important to make sure if you're climbing it that doesn't happen. A turnbuckle has a safety wire on it. Turnbuckle is used to tension a guy wire. And the reason that you use that is because wind tends to cause vibration. Vibration loosens things. When you're doing grounding is very important. When you're doing grounding, you want to follow all your local electrical codes. If you're going to be putting up a tower, you need a separate 8-foot ground rod for each tower leg, bonded to the tower and to each other, because lightning does not care. Lightning wants to take the fastest and easiest route to ground. And it's a lot better to have the lightning outside your house than inside the house. Lightning also doesn't like to go around right angles or sharp bends. So you want nice, gentle curves or straight lines for lightning to travel on when you're doing your grounding. And when putting in your grounds, you want to have all your grounds tied together with a heavy wire or conductive strap and never soldered. Why not?
Unsolder. It'll just go apart.
What'll happen?
It'll just come apart. It'll unsolder.
Why?
Heat.
Lightning is very hot. Yes, it will melt your solder. So that's why whenever we do grounding, if we're grounding a copper pipe or like a copper rod or a steel rod or something to a cable, we either use mechanical clamps or we do something called CAD weld, which is basically like what they use on railroads for joining railroad ties together. A lightning arrestor is a device that is in line with your coaxial cable with the center conductor, except that it has a gas-filled tube that under normal operations is inert and doesn't represent any kind of path to ground. But if there's a lightning strike, it ionizes the tube, causing a plasma. Plasma can carry a current, which carries, hopefully, the current and the voltage to ground, to the shell. So all of those go on a plate, they go outside your shack, and hopefully you prevent your equipment. If you know there's a thunderstorm coming, what's the best thing to do?
Unhook
everything.
Unhook everything. Yep, just disconnect everything. But we don't always know that that's coming. Okay, RF hazards and radiation exposure. Radio signals are what's known as non-ionizing radiation. To ionize something, a photon has to have enough energy to knock an electron out of its orbit and cause, for instance, if that happens inside one of your cells, that'll cause genetic damage. It'll actually do damage to the DNA. If you do damage to the DNA, you can have mutations. That causes cancer and all other kinds of terrible stuff. So, radio frequency does not have, not even microwaves, do not have enough energy to do that. So, we still, however, have to worry about radiation causing heating. Heating is the most significant reason that we do this. So notice we have this RF exposure calculator, and I'm going to put the link over here in the chat. This is a very useful tool to have. So let's say that, notice also in here we have our average power. What does average power mean? Everybody, what's average power?
Would that be RMS?
Well, it can be. What if you're transmitting 100 watts, but you have a duty cycle of 10%, which means you're transmitting for a minute, and then you're typically listening for 9? What's your average power?
10 watts.
10 watts. All right. So we have a 100-watt transmitter. We're going to assume a duty cycle of 10% in this case. So we have 10 watts. Okay, antenna gain. Remember what dBi is? It even says right here, enter 2.2 for dipoles, add 2.2 for antennas rated in dBd. That's that thing I was mentioning yesterday. Let's pick a dish. We're going to pick 30 dB, and we're going to be 6 feet, or in meters. We're going to be 5 meters away, which is about 16 feet, and we're going to be right in front of it. We're going to go 1296, and we're going to see if this will cook us. And is it safe? Here's a controlled environment, which means that everyone who is in that area knows whether or not it's safe. Uncontrolled means your neighbor is walking through and you haven't told them what you're doing. This says that, okay, here's my power density for that particular power level. And here's how far away you have to be in order to be safe for each particular case. So this is a 30 dBi antenna, and we're gonna go to let's go to 2396 for the heck of it, and we're gonna knock this down to like 2 watts. This is in the Wi-Fi. This is in the ham band right next to the Wi-Fi band. How much power are we running? 2 watts. That's not a lot of power, is it? How much gain do we have, though? We have a 30 dB dish. That is still at a distance of 16 feet unsafe for people who don't know what you're doing. You're only running 1 watt, but you're focusing it all in one direction. So that's why it's important to go through these calculations. That's why it's important to understand exactly what it is that we're doing. Okay, moving on. Who's responsible for ensuring that that no person is exposed to RF energy above limits? That would be the licensee. To determine whether or not your station is in compliance, you can use computer modeling. You can actually go walk around and use field strength equipment, or you can use those calculations. I think those little calculations with the calculator, they probably calculate worst case, but they're really easy to use. Somebody already did the hard work. Duty cycle, again, is the percentage of time that you're transmitting. It affects the average exposure to radiation. Duty cycle, if you have a 50% duty cycle, that means you can bump up your power by a factor of 2 and have the same overall effect. Why do exposure limits vary with frequency? Because people are resonant, as it turns out, that certain frequencies, because of the size of an average person, affect us in different ways. The worst case for people is at about 6 meters, at least for the ham bands. So what factors affect the RF exposure? Frequency and power level, distance, and the radiation pattern, which we experienced when we just showed that 30 dBd antenna or 32 dBd antenna. How can you relocate, or how can you reduce exposure? You relocate your antennas. Point them in a different direction if you can. Put them 30 feet higher. Get them further away from people who are walking by along the street. And how often do you have to do this? You have to do it whenever you change anything. So you put in a new amplifier, you put in a new transceiver, you put in a new antenna, you need to go through and reevaluate. Okay, let's see. Setups, station setup and operating controls. Okay, so we were talking about this a little bit yesterday. Big fat wires. Why do you use big fat wires? You minimize your voltage drop, right? Because big fat wires have lower resistance. They burn up less voltage. They burn up less power. You also want to keep them as short as possible. So fat wires and short wires. Okay, so now we're talking about efficiency. Okay, efficiency. So a 50-watt transmitter, right? A 50-watt transceiver. A transceiver is a combination of a transmitter and a receiver. How much power does it actually take to run a 50-watt transceiver? Typically, with RF circuits, we think of efficiency of about 50%. So to put out 20 watts, you would need at least 40 watts. To put out 50 watts, you'd need at least 100 watts input. And most power supplies are 12 volts. Now, that's a nominal voltage. An actual lead acid battery is 13.8 volts when it's fully charged. You can use 12 volts as a nominal value. So at that point, by Ohm's law, how much current do we need? What's that Ohm's law formula again for power?
E equals U or R.
P equals EI or IE. All right, and which one don't we know? We have power, we have voltage, so we don't know current. Current is equal to P divided by E, which is 100 divided by 12 is approximately 8.3 amps. And then you add a few amps here and there to run electrical circuits and turn the lights on and things like that. And what do you get? The most likely answer is a 12 amp power supply. That is a very common power supply to run a mobile radio. So when you're sizing things, it's really important to go through that process. Digital mode operation, you have a transceiver that has a speaker jack and a microphone jack and a push-to-talk line. Your typical computer has a speaker jack and a microphone jack, and depending on what it is, you need to somehow make it have a push-to-talk line, which will key the transmitter. So, what do you need? Receive audio, transmit audio, back and forth, and then some way to key the transmitter. For digital mode operation using FT8, where do you put the transceiver audio input? This goes to the audio input and output of a computer running the software. So basically, you hook up your audio in and out on your radio to your input and output of your computer. Line in on a computer is the same as a microphone input typically. All right, this is okay. So now we are into another area where I like to digress slightly. I know, just slightly, right? Okay, because this goes back to the physics portion of the class. So I am going to draw a wire, and the wire is going to be carrying current. Okay, what will be created as a result of carrying that current? What will be forming?
Magnetic field.
A magnetic field around the wire in loops. Okay, That is just part of physics. Thank you, Michael Faraday.
Flux lines.
Well, yeah,
Flux
but
lines.
you'll have flux lines, but we're just going to draw the magnetic field. It's going to be going around loops like that. Okay, so let's say that you have two different currents floating around. You have DC, and you also have this annoying IAC, which is going to not be, it's not going to be DC. It's going to be going like this, back and forth, plus and minus, plus and minus, plus and minus, plus and minus, making an oscillating magnetic field that goes back and forth along this entire wire. This is hooked up to a computer. Uh-oh. What kind of signals does your computer like to see? It likes to see DC, right? Let's say this is power. Your computer likes to have DC power, doesn't it? Look at your power supply. Your power supply will say 19.2 volts at 4.6 amps. And it'll say DC. Your computer does not want to receive AC power. That will cause it all kinds of problems. Well, let's say that you have a transmitting antenna up here that is generating RF. Is there anything keeping that RF from attacking and being received by your power cord? What is your power cord made of, after all? Come on,
Wire.
it's made of wire. Every single wire can function as what?
An antenna.
An antenna. Your wire will receive your RF signal. What happens if that RF signal gets into your computer? What will happen to your computer? Anyone ever have a computer, when you're transmitting, spontaneously reboot? I have. Have you had a keyboard become completely non-responsive? Or just enter into your computer G G G G G G G G G G until it overflowed the buffer? I've seen that. Or a mouse stop working when you transmit. All right. The reason that happens is because digital electronics that run on DC do not like AC. So we have fixes for this. There are ways to prevent this from happening. One of the ways to prevent this from happening is by
Toroid coil.
We're getting there. Okay, one of the ways to prevent this from happening is by doing this. Okay, so if I have a combination of AC and DC over here, and I use this, this inductor will allow what to pass through, AC or DC? Remembering it's just a piece of wire.
DC.
The DC will go this way. What will go this way? Down through the capacitor.
AC.
AC. I have now separated my AC and DC. This is known as a filter. A filter is a good way to separate AC and DC. If I'm really careful about it, I can pick the frequencies at which that happens, and then everybody's happy. Hopefully the computer gets exactly what it needs. However, sometimes you do not have this luxury. Sometimes you have this. You have this coaxial cable. Remembering that we have this thing called the skin effect, where RF frequencies travel on the surface of a piece of wire. How many surfaces are there here that can carry current?
2.
But it's insulated.
It's not 2.
1.
Nope, it's not 1.
It's 3.
It's 3. You have 1 right here, and you have 2, which is on the inside of the shield, and 3, because the RF doesn't care, you can have a different current on the outside when it's RF. You actually have 3 current carrying surfaces because it travels on the very outside. So if you have a properly matched system, the inside and outside conductors, or the inside of this one and this one right here, are carrying equal and opposite currents. Do they even know about this third current?
No.
No, they do not. Okay, so this is actually often known as common mode current. And this can actually be picked up by the outside of the wire and brought back into your station from the antenna. And then that gets onto the ground of the chassis of your radio and screws everything up, because now you have RF floating around on the chassis of the radio itself. I once had a situation where I had a microphone. So here's me, here's my microphone on a stand, and I'm talking into it, and I leaned up against it while I was talking. Man, I look terrible. I leaned up against it, and I got an RF burn on my lip. Why is that?
Didn't have an earthen ground?
That's exactly right. I was on the second floor. I actually had a ground wire that was about 40 feet long.
Ooh.
And I was on, let's say, the 15-meter band. 15 meters, that wavelength is about 50 feet. If this is grounded, that's at 0 volts. What is the voltage up here? The only thing that has to be true is that 0 volts has to be down here. By the time it gets up here, you can actually draw waves and see that this is not at 0 volts. My chassis was picking up RF from the cable, and it was not being properly grounded. There are 2 kinds of ground. There is safety ground or power ground, and then there's RF ground. These are different things. The higher the frequency you go, the trickier RF ground gets to exist. Because grounding requires you to be as short as possible. That wire should be as short as possible. Ideally, instead of 40 feet, how long should my ground wire have been?
50.
No, because 50, yes, that would be a tuned radial. That would be a tuned ground wire. But ideally, how long should my ground be?
60.
It should be maybe 5 feet. You want it to be as close to nothing as possible, so that you don't have any possibility of anything existing that allows you to not be at ground. Sometimes you won't have a ground wire at all. Let's say you live on the 12th story of a building. There's no ground. I mean, it doesn't exist. The whole building becomes an antenna at that point if you connect it all together. That might be good. That might be bad. So you have a choice. How do we prevent this from happening? Well, one thing we can do is we can take that signal that's coming down off the antenna or from wherever, and we can make it have a harder path to follow. We can take our cable and do this with it. This is called a choke. We can just basically coil up the cable a little bit, and it doesn't have any effect on what's going on inside it, but it takes the stuff on the outside, and it creates some inductance and a little bit of ability to block that RF from getting through. Essentially, we're creating an inductor. Another thing we can do is we can take that cable and we can take this donut-shaped thing and wrap it like this.
Yeah.
And this is known as a toroid.
Yeah, toroid.
And what this is a piece of metallic or a piece of ferromagnetic material that looks like this.
It's the same as ferrite?
Can everybody see that? Everybody see that thing? That is made of manganese or iron or nickel, or let's see, manganese, nickel, iron, and there's a couple others that you basically powder and bake into a shape with some glue. What's special about these is that they're ferromagnetic materials, which means that they react in such a way that they will tend to take the magnetic field that that current is creating and constrain it inside the donut. And the more times you wrap the wire around it, the more magnetic field gets constrained inside the donut. If you burn up the energy inside the donut as heat, how much of it gets into the radio? How much of it gets into your computer right here?
Zero.
Nothing, right? You can all look. Now this can also be built in different ways. This is a toroid. You can also take it and do this with it. Here's your cable, and you can do this.
I think you need to switch views.
Oh, you can't see that. Okay. There we go. There we go. You can take it and pass it through these little other shaped donuts, which actually look like this. They have a little hole inside, and pass it through and out the other side. And these are called ferrite beads.
Is that what this is right here?
That is exactly what that is. Can everybody see that?
It's just the one from my computer.
Yeah, hold on. I'm going to unshare. I got to do that anyway.
Oh, sorry.
Hold on. Okay, hold it up again. Hold it up there. All right. If everyone looks at your computer power cord, you will often see that there is something that looks like a little donut on the computer power cord. That is a ferrite bead. That is intended to choke out RF and make sure that any magnetic field that's created is completely contained inside that, thereby making your computer happy. So I have a USB cable that I run into my computer from my radio, and what I found is that I needed I ended up with the computer completely losing its connection to the radio every time I keyed up the radio. Kind of doesn't work, right? It's not what you want. Well, I tried ferrite beads. I started with one. I wrapped it around it twice, actually, and it didn't work. So how did I fix it?
Added another.
Added another one, and that one still didn't work. So what did I do? I ended up with 5. Right? Wow. When I got to 5, there was enough of it gone that the computer didn't lose connection with the radio anymore. So a lot of this is experimentation. You find out what works by figuring out what works.
Haven't you tried just wrapping it through a toroid?
I didn't have a toroid handy. But the other thing is that sometimes you have to look at the cable itself and look at the bending radius and see what's even possible.
Right.
So
right, that's true.
And the fact that the cable might not be long enough to typically, if you wrap it through a toroid, it ends up going the inductance, the impact goes up as the square of the number of times you go through it and make a complete loop. So doing it twice is a lot better than once, and doing it 3 times is a lot better than twice. 4 times is a lot better than 3. At some point, it doesn't work. It doesn't go up anymore. You basically saturate it, and it doesn't do any good.
Was there some way for you to measure that?
I mean, I'm sure I could. There just wasn't any point. I just wanted it gone. So, okay, so if we're looking at grounding and bonding, which one do you think would work better for carrying more RF current? A wire that looks like this? Here's the cross section. Or the same amount of wire, which is now smashed into a flat plate? Same amount of material.
What?
Why?
What's the skin effect?
Skin effect. RF travels on the surface. This has more surface area. So you take it, you squish it flat. It has more surface area. It can carry more current, less resistance. When you hook up a mobile transceiver, you want to go to the chassis ground. The reason you go to the chassis ground is because you want to provide as direct a path back to the battery as possible. Now, it is also true that when you are, let's say, looking at your car, you have a situation where, let's say, okay, if you look at how a vehicle's electrical system is built, here's your plus and here's your minus, and the minus is connected to the chassis and it's connected to everything, and here's the hood and the trunk, and there's the wheels, and they don't do much of anything for this. They isolate it from ground, but basically the whole chassis is grounded together, right? So if you have a relay here that turns on your headlights, it goes like this. Here's your headlights. There's your headlight. Where is the negative terminal wired back to?
The closest hunk of metal.
The chassis. Because why would you want to waste extra wire going all the way back to the battery? Isn't that just a waste of copper?
Yeah.
Okay, so how much current is the chassis capable of carrying from any given point? And the answer is, I don't know. I have no idea. It depends who built it. It depends whether the robot that built it was feeling good on that weld that day, right? It might be holding everything together, but is it capable of handling 22 amps? I don't know.
Full frame, yeah.
No idea. So if you're hooking up a radio in this car, what you do is you ignore the entire electrical system. You just imagine it's not there. And you have a battery. And you take your radio, and your radio is up here somewhere like this, and you hook up the plus to the plus and the minus to the minus. All the way back at the battery. You want those connections to be short and fat, just like always, so that when you go to pull current, you don't have a lot of voltage drop. Remember I said that most problems come back to Ohm's law? You find that when you key your radio, it turns off. Why is that?
Couldn't provide the current.
Couldn't provide the current. And let's say that you have a high resistance, and you're now switching from pulling almost no current to pulling 10 amps.
Making heat.
And you pull 10 amps across a 1 ohm resistor, which is basically like a crappy piece of wire with a bad connection, and you're dropping 10 volts across it. How much voltage is your battery in the first place?
12 something.
12 volts. You lost how much in the wire? 10 volts. How much voltage is left to run the radio? Is 2 volts enough to turn the radio on? So the power turns off. And then when it does that, it turns back on because you're not there, because you're not pulling the current anymore. So you want your connections to be short and straight and as big as possible.
Question.
Yep.
When hooking up your radio directly to your battery, when you turn your car off and you don't turn the radio off,
yes, you can drain your battery that way.
Okay.
I have done that. Yes. So I have done that. So you need to be careful. So
I always use SB connectors, if you're familiar with those, and 4-aught cable.
Oh, those are huge. Yeah, I don't use anything that big. But the other thing is you can actually wire an auxiliary relay through the ignition switch to kill the power to the radio when you kill the ignition. So how do you determine the length of time? Let me switch to the right thing.
I have a question. So I had a call, so I missed. You may have talked about this. Did you talk about electric vehicles? What if you put a radio in an electric vehicle?
I did not.
That's what I have. I have a Volt.
That's another question altogether. I mean, if you have 12 volts available, it should be fine. If you're not pulling too much current, you take a look at the cigarette lighter adapter. It's probably enough current to get away with. You really need to look at the ratings though. There's also probably a 12 volt bus available somewhere that can carry more current, so you want to go to that. And no, I didn't mention electric vehicles. That's a really good question. Okay, how do you determine the amount of time that equipment can be powered from a battery? Batteries are rated in watt hours and amp hours. Amp hour and watt hour are related together because a watt is an amp times a volt. You have to look at the voltage of the battery. But essentially, if you have a 10 amp hour battery, and that means you can supply 1 amp for 10 hours, or in theory, 10 amps for 1 hour. You just multiply the two. Okay, operating controls. 5-minute break, everyone?
Sure.
Okay, 5-minute break.
1 minute break.
So are they going to give you a lunch break, or?
At the end of the class, we have 1, and the exam's supposed to start at 1. I haven't figured that out yet. Oh, I know. I got an email from the exam people in Alaska, and I didn't want to listen to it or read it when he was talking. Bye. Bye. Oh, I would be happy to go eat again the same menu in AGM. I need to pork again. Look it up. There's no new menu anywhere. Yeah.
Boop. All right, I'm back to answer questions before we get started. If anyone has any.
Your exam test session. My name is Dave. My call sign is N4NG, and I will be explaining the testing interface so that you can successfully pass your exam with the least amount of stress. So what I want to bring your attention to is
Okay, everybody ready to get going? Is this thing on?
Yeah.
I have a question.
Uh-huh.
I have a Mazda, and if I leave the charging cable to my phone plugged in, but I don't have the phone on the cable, it drains my battery and I have to have it jumped. I don't understand why that happens.
Say that again.
Okay.
If you
I have a charging cable for my iPhone. I left it plugged in to the car whatever you call that, jack.
Mm-hmm.
But I took the phone off of it, so I figured I was removing the source of the drain.
Yep.
But I wasn't. And so 3 times it took me going on to Google and finding other people that have Mazdas and that has happened to them. So I have to take the whole cable and unplug it as well as my phone.
That is very weird.
No,
I thought so.
I know what's going on. So what's happening is over Mazda and the power supply, that adapter thing doesn't time out. And because you have the power adapter plugged in, you're keeping the ECM alive. And it's staying.
Oh, is that it?
It
senses it needs to be? Okay.
And it's drawing down your battery. So, yeah, you can't do that.
Yeah.
So it's not the cable itself. It's the electronics in the car.
Right.
Interesting
anyway.
and kind of weird.
But I did learn how to jump for my own car.
Yeah, great.
A little gizmo.
Okay, so I wanted to point out that notice with regard to ferrites, they are, well, look at that. Your ferrite inductance is measured in, see that letter H? What units is that?
Henrys.
Henrys, yeah. Okay, because it's an inductor. And it has a rating in frequency, and then you also have this thing called a mix type. Different mixes of materials are centered together and produce different frequency responses. So ferrites show up literally everywhere in electronics. If you look at Ferrite, that's the name of the company that makes them. They are the biggest manufacturer of ferrites everywhere in the world. And look, they even have a video of ferrites coming out of the oven. So, very cool stuff. And if you want to play around with some ferrites, you can actually, or you can actually get like a sample kit from them, I think. So, okay, so here we go. Now we're on to operating controls. Well, okay, operating controls. So you have effective microphone gain. What happens if you have too much gain? Your voice is too loud. This is the answer to almost everything. You get distorted audio. If you're transmitting above or below a signal's frequency, you get distorted audio. If you're on FM and you're yelling into the microphone and it's over deviating, you get distorted audio. Yeah. Okay. To enter an operating frequency, we're going to go to this nice convenient SDR. And notice we're on the wrong mode. We're on AM. We're going to go to up. We're going to go to lower sideband because it's nighttime in Europe. And we're going to go to 7150. And we should find it. There we go. So, think of this as a transceiver. You just punch in a frequency. All right, so that's a nice little frequency control. There's also usually a VFO tuning knob available. This doesn't have a tuning knob, but most radios also have a tuning knob. You can also, on most radios, store the frequency in a memory. Most handhelds, even very basic ones, have at least 100 memories now. Some of them have up to 1,000. A lot of frequencies to store. Okay, what? Oh, shoot. Why are you behaving like that? The scanning function of an FM transceiver allows you to scan through a bunch of frequencies in rapid fashion so that you can figure out what you want to listen to. Squelch. All right, we're going to show you what squelch does right now. I know this has squelch. You just hear noise. There's the beauty of squelch. So if there's nothing to hear, the squelch mutes the receiver. If something comes back, it will break the squelch. We use this on FM a lot because, especially on repeaters, the signal's either there or it's not. If we're doing weak signal work, you basically open up the squelch all the way and listen to the static because you're listening for something that is hovering just above the noise. Repeater offset. Okay, repeater offset. It is time to start drawing our first repeater. And we have 1 hour and 20 minutes left, so we're going to hoof it and we're going to make some hay as they say. And here is our repeater. So we have this thing called an RX, which is a receiver, and a TX, which is a transmitter, and in the middle we have a controller. And what happens is the controller is essentially a computer. The receiver is hooked up to an antenna. The transmitter is hooked up potentially to another antenna. Not necessarily. It could be the same antenna. The audio from the receiver goes through the controller, and it is then decided whether or not it is forwarded along to the transmitter to be retransmitted on a different frequency. The key is that there is something called an offset. The repeater will be transmitting on the published frequency. So let's say that it's 145.45 megahertz. The offset on the 2-meter band is 600 kilohertz, either plus or minus, depending on which one you're looking at. Which website are we talking about? Oh, Fairrite? Just type in FAIR-RITE. Okay, so that also means that the receiver is going to be operating 600 kilohertz away. Because this frequency right here is below 147, this one is going to be a negative offset. So you will be at 144.85 megahertz. Oh, it's WebSDR. That's just WebSDR. And it's the University of Twente. So this basically provides the receiver offset that we're looking for so that the transmitter and the receiver don't interfere with each other. When you key up your radio, if the offset is programmed correctly, will change your frequency automatically so that it's transmitting on the frequency that is necessary to access the receiver. There is another thing. So there's something called an offset. That's either plus or minus. Again, on the 2-meter band, the offset is 600 kilohertz. On the 70 centimeter band, it is 5 megahertz. So there's another thing that we have to do. We have this thing called squelch. And there are a couple of special squelches. One is CTCSS, which is a tone, a subaudible tone that is transmitted along with your voice. The other one is called DCS, which is digital code squelch, which is a tone sequence that is transmitted along with it, along with your voice. If the receiver is not designed on the repeater to receive the proper to receive the same tone or sequence that you are transmitting, your signal will be received but then rejected by the controller. At which point it is not retransmitted and nobody will hear you. So if nobody can hear you, what does that mean? You have the offset wrong, or the CTCSS, or the DCS wrong. So those are the things that are most common to happen. You basically not set up your receiver, your radio correctly. The benefit of a repeater is that repeaters are often placed in very advantageous locations, whereas you might not be in a very advantageous location. So let's say that you're in the woods and it's hilly and stuff like that, and there might be a lake nearby, but let's say that you are down in a valley. And so here I'm going to draw myself. I'm going to put myself right here. All right, with a handheld radio. And it might be that I am trying to talk to somebody in the next valley, and they cannot hear me at all because there is a mountain in the way. This is very common, especially if you live in Oregon where we have a lot of mountains. Let's say, however, that you have been you've had a lot of foresight and you built a repeater station that is up here on this mountaintop. VHF and UHF usually follow line of sight, which means that if I am able to transmit and be received by the repeater will then, if I've set it up correctly, take my signal and put it on another frequency and retransmit it in all directions. So to the rest of the world, where does it sound like I am standing?
On
Up a mountain.
On top of a mountain, yeah. So, okay, so now we take another person, we put them way over here on this hilltop with a handheld radio, and we can talk to each other. Take somebody else who's down here with a handheld radio, and we can talk to each other. And in fact, everybody, because they are all in mutual range of that repeater, they're all line of sight, can all talk to each other. There's also something we can do called linking, which is where, let's say there's somebody else. We're going to take this person and put him down in a valley, where now he's down here with a handheld radio, and he can't hear anybody. But we're going to add a repeater system. We're going to put another one up here. And we're going to make it so that there is a backbone linking these two together, so that everything that is received by one gets retransmitted by both. Well, now this person can access this repeater. By virtue of that fact, they now access both repeaters, and everybody who can access both repeaters can now talk to each other. So all of these people are now in mutual communications range. And
What
that
did
is
you
it.
call the red line? Would you call that red line?
That's a backbone. That can be over the internet, that can be microwave, that could be UHF, it could be any number of different things.
Scott, I got a question.
And this
Might be a little
is
bit
called linking, by the way.
might be off topic slightly,
Okay.
but in order to do that, so the repeater is reversed on the frequency, correct?
Correct.
So
yes.
Then wouldn't you reverse that for it to link?
You'd typically not even bother with that because you don't want them directly linked on the outputs. You'd have a backbone channel that is just sharing the audio back and forth.
Okay.
Totally different set of frequencies.
And that's totally different than group talk.
Yeah.
Oh, yeah.
Yeah, that's
So
totally
is there a published list of repeaters somewhere? Like Scott, you and I
that's
are
a good
getting
question.
close to each
Yeah.
other. Don't we have a repeater over there in the South Hills or something?
We have dozens. So there's a site, which is, I'm going to anyone ever visited this?
Yes.
Repeater book. This is a worldwide listing of all the amateur repeaters that are out there. And that means everywhere, every country, every state, every city, everything you can think of. And so you want to do a search. This will allow you to find, and in a lot of cases, map repeaters. And on top of that, a lot of them are actually internet linked as well. And because of that, you can then take an app such as EchoLink or Allstar and connect to the internet link. So if there's a decent internet connection, you can actually connect to the repeater and then use it as though you're a user on the repeater.
Question.
For Android, there's also an app available for the repeater book.
Oh yeah, I have it on my phone. That's actually one of the first things I do when I land somewhere for the first time.
Is there a resource that we have received a good variety of websites, that you were using for the HF stuff and for the VHF and whatnot, that lists all those resources that we could access? I mean, because there's a lot that you've given us just in this class.
Yep. I mean, I suppose I could put together a link, put together a pile of them. I can't.
But I mean, is there a general link?
I don't have a general link. No. I mean, somebody might have one out there. I've never found one.
Gordon West has a book that has many, many links in it.
Go ahead, Kent.
Well, just for one comment on that point. Listen, this is a massive field. There are hundreds of thousands, millions of hams in the world. So there are tons and tons and tons of resources out there. So Google is your friend. Fellow hams are your
Yeah.
friends. Your clubs are your friends. That's the way to find stuff. There's lots and lots of things. Scott, I was looking for Philip Powell. Is Philip in your class today? Philip Powell? I don't see him. I tried to DM him. I don't see him here. No?
I don't hear a response.
Okay, guess not. All right, guys. For those of you who are testing, wait for our phone calls. We'll see you in a little while. Good luck. Thanks, Scott.
It's still an hour and 20 minutes away. So hour and 10 minutes.
Yeah.
We've still got a lot of material to cover. So.
We're rounding up our posse at our end, getting ready. We've got 24, 25 VEs ready to help out.
Make sure you send a note to Hannah if you haven't done so. She needs to be.
I've not. She needs to.
Yes, I know. It's time for her to do it again.
Good luck, everybody.
Okay, let's see. Scott. Thanks, Kent. All right, let's see. Digital voice. Okay, a talk group. This is basically, there are multiple talk groups on a digital repeater. You can actually link those repeaters together. If you are in a talk group, it acts as though you are all in the same area, able to talk to each other. One thing about it that's cool is that it uses the internet and voice over internet protocol for linking voice from repeater to repeater. And it basically creates a very, very large worldwide repeater system. How do you join a repeater's talk group? You use the group ID. A DMR code plug. I don't know why they call it a code plug. This is basically just in a local area. It's all the information for all the repeaters and talk groups. I don't know why they call it a code plug. It's kind of a weird name. But it's easy to remember because it's weird. Specific group of stations connected on a digital voice transceiver. You enter the ID code and it acts as though you are all within the same area. All your voices are forwarded to everybody else. Color code. The color code matches. A repeater has a color code. You apply the color code and you can access the repeater. D-Star is a competing technology to DMR. DMR is digital mobile radio. D-Star is something that was developed by ICOM and adopted by Kenwood. One thing about D-Star is that it also transmits your call sign when you key the radio, so the person automatically knows who you are. It's just another competing technology. Yaesu has another one called Fusion. It's like the beta versus VHS. They all work, but they don't talk to each other, unfortunately. Multiple receive bandwidths. Okay, so what we're going to do is we're going to take a look at this. And everybody can hopefully hear that. Okay, so what we're going to do is narrow out we're going to narrow down the receive bandwidth. Unfortunately, we're going to narrow it down so much that there's so much of the voice missing that you can't tell it apart. So for voice, we would typically go for 2.4 kilohertz. That's an appropriate bandwidth for voice. However, if we go down to Morse code and we see that there's this contest going on and we take a look at our bandwidth, how many signals are within that yellow stripe?
Yeah, 5. 6.
5 maybe? And here's what it sounds like. Okay, so I can work with that, but I'd prefer not to sometimes. I can do this. This is filtering. This is a digital filter. You can also do filtering with a crystal. You can do filtering with capacitors and inductors. This is the basis of filtering. You can basically selectively pick out the thing you want to listen to. So This is about 500 hertz nominally. 500 hertz is a good fairly narrow filter for listening to Morse code. If I try to open it up wide again, I'm basically overwhelmed with lots and lots and lots of signals, and I have to do all the filtering with my ear. Trust me, after 48 hours of this, because this contest is 48 hours long, that would get pretty fatiguing. Okay, there's also something called a clarifier. Okay, so we're going to clarify one of those voice signals. So let's go back to a voice signal. A lot of Russians out there today. Okay, so we're going to find a nice voice signal to listen to.
How can you tell that they're Russians? Just
because I know the call
obviously
signs. Call signs.
Oh, through the Morse code.
Yeah. Okay, so let's say that I tune somebody in, and when they call me back, they sound like this. Well, in a transceiver, that's a transmitter and a receiver, they are based on a common single frequency. Well, if for whatever reason on the other end of things I sound right, but the other person sounds like this on my side, I have to split them apart. There's something called a clarifier or receiver incremental tuning. I'll pick another one. That, let's say they sound... Sorry, you can't predict when people are going to show up. So if they basically don't sound right, like that, I can tune so that they sound right without altering my transmit frequency. So basically that allows us to account for drift in one person's transmitter or receiver, or just like a dial inaccuracy or something like that. So that's known as an RIT or a clarifier. To key a transmitter, you have this thing called PTT, which is push to talk, which grounds a wire and switches a transistor, which switches the radio into transmit. Okay, a device that combines a receiver and a transmitter is called a transceiver. A device that switches RF input and output of a transceiver to another band, it's called a transverter. In a way, a repeater functions as a transverter, although the input and output frequencies are very close to each other. So, what device increases the amount of transmitted output power? That would be a power amplifier. If you have a single sideband CW FM switch on a VHF power amplifier, that is because it is there because you want to select the right mode of operation. This goes back to our drawing of a transistor from way back when, yesterday, when we looked at the input-output curve of a transistor. This is the linear region. If you're doing single sideband, you want to be using this linear region, and it biases the transistor and shifts it so that it's using this range of the transistor. It's not very efficient because when there's no signal, the transistor is still powered. FM is basically a signal that is either on or off. So you can actually use these more efficient parts of the transistor frequency curve for FM. Same with Morse code. Same with CW, which is Morse code. So the single sideband portion, that if you throw the switch into that mode, the efficiency goes down, but the linearity goes up, which is something you need. Okay, let's see if I can do that. There we go. Here we go. I always like doing this one. Okay, what term describes the ability of a receiver to detect the presence of a signal? That is sensitivity. If somebody whispers, for instance, you can hear the whisper. That would mean your ears are sensitive. Selectivity means that you can pick out one signal in a crowd of signals. So let's take a listen to this again, and we're going to unmute this. Is that a particularly selective receiver right now?
No.
Nope, not at all. However, what if I do this? That is now very selective. I've increased the selectivity of the receiver by changing the bandwidth of the filter. You guys get the feeling that filtering is important?
That's what we do.
Yeah, filtering is and what's the basis of filters? Two devices. What are they again?
Inductor and a capacitor.
Inductors and capacitors. Yep. That's it. Those are the basis of filters because they're frequency sensitive devices. Okay, an RF preamplifier is something that goes in the receive line that is designed to make signals bigger, make a bigger copy of a signal before it gets lost completely. This is typically used in a cable TV system, for instance. They might put a booster out at the box so that by the time it gets to your house, there's enough signal left for you to not get blocking on your TV. Something that moves a frequency from a signal from one frequency to another is known as a mixer. That's a nonlinear device. And something that creates a frequency at a signal at a given frequency is known as an oscillator. There are things called direct oscillators, I guess, direct digital synthesis, which is not really an oscillator, but allows you to generate a particular frequency by using a digital process. But if you look at this thing called an oscillator, that is basically a tuned circuit which uses, in a lot of cases, two devices. What are they?
Inductor and capacitor.
Inductor and capacitor to amplify a particular signal that you have chosen to amplify. There they are. They come up over and over and over, don't they? Okay, the act of changing a signal and modifying it by another signal is known as modulation. Okay, let's see where we are. Okay, so now we are into filtering because the section is called Symptoms, Causes, Cures of Common Transmitter and Receiver Problems. Interference. Okay, there's a couple of things that can happen with interference. Number one, there can just be another signal nearby that is so big that even with all the filtering in your receiver, you're going to hear it anyway. Right? There was this radio station near where I was growing up, and it was about 2 miles away, and it was transmitting with, I don't know, 10,000, 15,000 watts. It didn't matter what my radio was tuned to. I heard it anyway. That's fundamental overload. A harmonic is just like in music. It's an integer multiple of a frequency. So if I'm transmitting at 10 megahertz, I get harmonics at 20 and 30 and 40 and 50. If you're building your own transmitter, there are requirements for how far down in decibels below the fundamental those have to be. Another reason to learn why you have to learn to take this class. Why you need a license. Spurious emissions are frequencies that are generated that don't really follow any pattern. They just happen to show up. So if you have a transmitter and it has a capacitor and an inductor built into it, which most of them do as part of a filtering circuit, could you be unlucky enough that you have those go into oscillation?
Oh yeah.
And if you have a capacitor and an inductor, what frequency are you going to be operating on? It's the one that's defined by the filter components. You're not really sure what that is. It's just going to oscillate wherever it sort of feels like it. That's known as parasitic oscillation. Okay, your neighbor tells you you're interfering with their cable or TV. Your cable TV or their phone or something like that. What do? You transmit, you check your own equipment first. Well, if your phone is not being interfered with, your TV is not being interfered with, you've checked that, then you can go to the neighbor's house and say, okay, there's something wrong with your TV. And go try to help them out. What's the first thing you do? when you find that a cable TV system seems to be getting noisy and not receiving your pictures properly, you go and check all the coaxial connectors and make sure they're tight. A leaky cable, a leaky connector will cause all kinds of problems. A broadcast AM or FM radio that receives a ham station, well, they have nothing to do with each other. They're not in the same frequency band. But if a transmitter is not built well and it lacks a certain thing that starts with the letter F, which is called, somebody give me the word.
Filter.
Filtering. If it's lacking filtering, then it can be beaten up by a nearby signal that has nothing to do with it in the first place. Well, okay, how can fundamental overload of a non-amateur radio or TV receiver by an amateur signal be reduced? Well, what would you put in there?
Filtering.
A filter. Wow, that keeps showing up, doesn't it? You getting the idea that filters are really, really, really important?
Not a high pass or band pass filter?
Yeah. Okay, so which of the following can reduce overload of a transceiver by a nearby commercial FM station? You install a band reject filter. Okay. Used to be that if you had, is anyone old enough to remember when AT&T owned the telephones in your house and you just rented them?
Yeah.
Okay. I remember that. Okay. If you had a ham station on your block, or let's say it was yours, and it interfered with the telephone, do you know what the phone company would come and do? They would put a
filter.
They would give you a filter and come and install it at your home and put it on your phone so that you didn't interfere with them. Because if your phone doesn't work, they don't make any money. So,
hey, Scott?
Yeah.
There's an interesting corollary to that that has to do with FCC rules and generating interference.
No, we're getting there. We're getting there. That's next. That's next. And we're down to 56 minutes to go.
Okay.
But I'm getting there. Okay. So if something in your neighbor's home is causing harmful interference to your station, okay, this is exactly what Bruce was starting to say. There is something called, that we live in, there is a section of the rule book called Part 97. Part 97 is the ham radio rules, right? This governs transmitter power, this governs harmonics, it governs spurious emissions, it governs everything. It's all in Part 97. When you get a ham license, it's governed by Part 97. When you get a transmitter, when you buy a transmitter or build a transmitter, it's governed by Part 97. There's another part called Part 15. Part 15 is unintentional radiators, which is your computer, your iPad, your cell phone, my exercise bike, my TV. Those all have oscillators in them. They all have tuned circuits, but they are Part 15 devices. They are unlicensed devices. Part 97, if you have a ham transceiver that's been designed properly, it is a Part 97 device. There's also Part 95, which is CB and FRS. There's Part 90, which is commercial band radio. Those are all services. Those are all parts of the FCC rules that govern how equipment works. Part 15 is a catch-all to cover everything else. If you are operating and you are within specifications operating a ham radio and somebody's TV next door decides that it doesn't like it, whose fault is it?
They're following the rules. It's their fault.
That's right. It's their fault because that is a Part 15 device. A Part 15 device, for instance, let's say that somebody has a grow lamp, right? They've got a pot grow in their basement, which is legal in Oregon. They've got a pot grow in their basement. They've got a certain number of plants, and those power supplies are generating RFI that is affecting your ability to receive the amateur bands, and you are a licensed ham radio operator. Whose fault is it?
Their fault.
It is their fault. That's right. You could go to the FCC eventually and say, they are interfering with me and we need to make them stop. it's easier to work it out on your own. But essentially, a Part 15 device must accept all interference from licensed services and must not interfere with any other licensed services. It is up to the owner of the thing that is covered by Part 15 to fix the problem. You can help. It is not your responsibility to do so.
How would they fix it? With a filter?
You could do a filter. They could also throw it out. I mean, that's the solution. That's a solution with a lot of grow lamps. They just
Scott, you're correct when you say that it's not your responsibility to help. However, especially historically, when we had old-fashioned TVs, when amateur signals would often cause the screens to go jaggy. In those cases, those rules still applied, and it wasn't the job of the amateur radio to solve it. But in good conscience and as part of the ham radio community,
you want to be neighbors. Yeah,
you want to be neighbors. So you would offer to help solve that person's problem, even though it was not your fault.
That's right. You still want to be neighborly. It's good optics.
The biggest offender I have around here is my switch mode power supply for my very expensive Nordic Track treadmill.
Yep, not a doubt, without a doubt. There are very quiet switch mode power supplies, and there are very noisy ones.
This one's very noisy.
I recently built a new computer, and I bought what I thought was a decent power supply for the box. I plugged it in, and my screen on my radio went absolutely nuts.
Yep.
So I sent it back, and I spent more money on a better box, and all that noise went away.
Okay, next we are on. Okay, what can be the problem if you receive a report that your audio signal through a repeater is distorted? You're in a bad spot, your batteries are running low, and you're not able to transmit properly or function properly. You're not deviating properly. Or you could be off frequency. Or you could be talking too loud. If you're talking too loud, you're going to over deviate, and people will not be able to hear your entire voice, and there's parts of your voice missing, which makes you sound distorted. If you're doing digital signals and you're in a bad spot, what you'll end up with is that you will have high error rates, and you'll have a lot of repeats, you'll have dropped connections and things like that. If you're over deviating on a handheld radio, most handheld radios don't have mic gain. The mic gain is how far you're holding the radio from your face. So if you're screaming into the microphone, you can quiet down. If you're too close to the microphone, you can get further away. If you're too far from the microphone and people say you need to speak up, you put it closer to your face. Test instruments and soldering. A multimeter measures voltage and current and resistance typically. To measure electric potential, that is volts, you use a voltmeter. To measure current, that's amps, you use an ammeter. To measure resistance, that's ohms, you use an ohm meter. To use a voltmeter, you would put it in parallel with the circuit. If you put it in series with the circuit, you will not have a voltmeter anymore. An ammeter goes in series with the circuit because you want to actually see how much current is flowing through everything. If you select the wrong setting, you can say goodbye to your meter. If you are lucky and you have a Fluke $500 multimeter, it has a fuse in it that you hopefully have a spare for. It's a 440 milliamp fuse. And hopefully that blows and saves your meter and then allows you to, I have done this once. And so you end up replacing the fuse instead of replacing your $500 meter. When measuring high voltages, okay, that Harbor Freight meter that costs $3.99, would you measure 480 volts with it? In theory, it might work, right?
Mm-hmm.
I personally would not. I don't think the leads and the meter itself are probably rated to that kind of voltage, but my Fluke is rated to 1,000 volts.
There's no VTVM.
Is that a VTVM?
Yes, and I use it still.
Vacuum tube voltmeter.
Very accurate.
An ohm meter is connected in parallel with a device, but it's important to note that What is Ohm's law again? Everybody, give me Ohm's law.
Equals I times R.
Everybody.
E over I times R.
No. E equals I times
E
R.
equals I times R.
Okay, E equals I times R. Good. Okay, so if you don't know a magic resistor, right, what you do is you take it out of the circuit and you put a test voltage across it, and that generates a current, which then you can measure. If you know what the voltage and the current are, then you can figure out what the resistance is. That is what a multimeter does when you measure ohms, when you measure resistance. The reason that you take it out of the circuit is because you're basically looking at measuring a voltage and a current, and you don't want another power supply or another device in the circuit to affect your reading. So it's kind of a pain, but you have to actually at least remove one of the leads of a resistor in a circuit, for instance, if you want to check. If you find a large discharge capacitor, what will happen is when you try to take the measurement of the resistance, it will start at 0 and it will go up to infinity as the capacitor charges up. To measure electric current, current is in amps. You use an ammeter. You put it in series. We only ever use this thing called rosin core solder. Notice that this says which of the types of solder should not be used. Should not be used. Acid core is for doing things like plumbing. It will eat through a circuit board. You do not want to do it.
That's an example of a trick question that the test tries to trip you up on.
Yeah, there's only one. And it's probably not going to be on your test. So what is the characteristic appearance of a cold tin lead solder joint? Okay, a cold solder joint is typically, in order to make a good solder joint, when you connect two wires together, the wires themselves end up being hot enough to melt the solder directly to the wires. That is a nice solder joint. It is possible, however, to use the iron to just melt the solder and have it flow across a wire without actually making a good electrical connection. That's a cold solder joint. What happens typically then is that at the most inopportune time, it will decide that it's going to fail. And then your thing won't work anymore. So if it looks lumpy or rough or not shiny, that could be a bad solder joint. All right, operating procedures. Type of amateur station that simultaneously retransmits the signal of another one. That would be a repeater station. It literally takes a signal in and repeats it. There are other stations that do the same thing. An auxiliary station can be a store and forward kind of thing. It can also be a backbone link between linked repeater systems. A space station is anything that is 50 kilometers or higher above the surface of the Earth. That can also function as a repeating station. Okay, a linked repeater network is something we discussed. Basically, if you have multiple repeaters that are sharing the same audio, you'll end up with a link between the two. The frequency offset in the 2-meter band is 600 kilohertz. The frequency offset in the 70 centimeter band is plus or minus 5 megahertz. We covered CTCSS. That's continuous tone carrier squelch system. We also have this thing called DCS, which is digital code squelch. If you have the wrong DCS or CTCSS or the offset, there are your things. We have multiple different nets. We have beginner nets in Eugene. These are the things that are usually wrong. You managed to got the wrong offset, either the wrong direction or the wrong number, or you got the wrong tone or the wrong code, or you forgot to put it in. A reverse function allows you to flip the receive and transmit frequencies temporarily. That allows you to listen on the input frequency of a repeater. It might be that somebody you know is nearby and it turns out that you want to talk to them and they're right across the street. Why tie up a repeater, which is a useful resource that everybody can use if you're just right across the street from each other? What causes you to be distorted on voice peaks? If you're talking too loudly, that basically over deviates your signal. It gets too wide. If it gets too wide, you get cut off. W7BTM, N7JI.
Yes.
Well, you're supposed to answer me. How do you answer me?
Oh, N7JI, W7BTM.
There you go. Okay, you say the other person's call sign first, followed by your own. That's how you call somebody on the air. Don't do it the other way. If you want to say that you're listening on a repeater, you would say the word monitoring or listening, N7JI listening. If you're operating on the same frequency as you're transmitting, receive and transmit, that's known as simplex operation. We don't do this thing called full duplex. Full duplex is where you can hear and talk at the same time and they don't interfere with each other. Duplex is where you're using two different frequencies, but we never really do that a whole lot. I mean, repeaters do that. That's actually more of a half duplex though. So simplex is when we do that. So we have designated simplex frequencies. The national calling frequency is 146.520 megahertz. Everybody who has a radio that is scanning the band will be listening on 146.52 at least some of the time. That's sort of like the national, it's called the national calling frequency. Okay.
You're driving down the road with one of those and you want to see if anybody's out there, you would pick it up and turn it to that frequency.
There's often somebody in almost every town who is listening to that. The meaning of CQ, we're on to the HF band. CQ, CQ, CQ. That means I'm looking for somebody to talk to. Some people say that's actually like, I seek you. I'm looking for someone to talk to. What do you do before calling CQ? Well, first of all, you got that frequency spectrum chart that has all those allocations in it. You don't necessarily have all of them. You need to make sure that wherever you're going to transmit, you're allowed to. And then you listen, make sure you don't hear anyone, and then you ask if you hear anybody, if anybody can hear you. Why would you need to ask? Why would you need to ask if anybody's using the frequency?
Because sometimes you can't hear what is going on the other end.
Yeah, you can't hear the other stations. So let's say you have station A and station B and station C. And station B and C are talking back and forth. And at this particular moment, station B is doing all the talking. And you cannot hear station B because you are too close. And you say, I wonder, can anybody hear me? And you're asking the entire world. You haven't heard anything, but station C has been listening to station B talk for the last 3 minutes.
Hey, Scott?
Yep.
It's possible that some of the folks were confused by some of that. You said that if you're station A and station B is transmitting, you might not hear him because you are too close.
Yeah, we covered that yesterday.
Okay, never mind.
It's just radio etiquette.
Yep, you're inside the skip zone. So basically you're going to say, hey, can anybody hear me? Am I interfering with anyone? And station C, even though you don't hear station C talking, will probably tell you, yes, I'm in the middle of a conversation. Thank you. Okay, so that's a good example of where the skip zone comes into play. All right, let's see.
So Scott.
Yes.
That was HF.
Yep. It can also be it can also happen on VHF.
Okay, and my question is, on repeaters, do you still ask?
No.
Okay, so that is this frequency in use is not necessary on a repeater.
No. I mean, you can, but if you don't hear anybody, then no one's using it. The thing is, the assumption is that a repeater is going to exist. If you're on a frequency that you know a repeater exists, the assumption is that the repeater exists because you know it's there. If you don't hear anybody, then nobody's using it.
Question.
Mm-hmm.
Um, suppose you know that there's a repeater, but you don't know that there is a tone squelch on that. You don't hear any conversation, um, and you try to. Is it
Go look at that's when you go look at the entry in the book.
right? But it's more like what they call kerchunking.
Well,
To see,
yeah, but you still want it. You still need to throw out you still need to throw out your call sign.
right?
But yeah, you're
But
basically saying, like, if I'm in another town and I want to know if I'm hitting a repeater that's listed in the book, I set it up and I just key and say N7JI testing. And if I hear the repeater, then I know that I made it. Does that answer the question?
yes, it does. It's just more like a lot of times I'll switch over and I'll just uh, do a quick key down to see if I open up the squelch on the repeater, and then give my ID
Right.
uh, if I hear that.
Ah, but you need to give your ID even if you don't hear that. Why is that?
That's the part. I mean, I would follow giving my, but thank you. That's a good reminder.
Yeah, even if you didn't hit a repeater, you still need to ID because there cannot be any what?
Unidentified
There
transmissions.
cannot be any unidentified transmissions. Exactly. Okay, so let's see. Next, one making on-the-air test transmissions. Yeah, there you go. You have to identify the transmitting station. Okay, Q signals: QRM, QRN, QSY, QRU, QSL. QSL means I confirm. QRM is man-made noise, in other words, interference from another person or station. QRN is static, typically from lightning storms and stuff. QSY, that means I'm changing frequencies. Okay, a band plan. Every area has a band plan that is designed to keep the sanity of everybody who lives there. They're amateur radio bands. We do not have frequency limits within the band. The FCC just says, with a very few exceptions, thou shalt stay within these frequency ranges, and that's it. Where you go, what you do in those frequencies, really, there's typically not anything written in stone legally that says you cannot use Morse code above out of a certain range, or voice outside of a certain range, or FM outside of a certain range. I mean, there is some stuff that's written into law, but a lot of it is not, especially on like 2 meters and VHF, UHF bands. So what there are band plans that basically are agreements between people who live in a certain area or in the United States or whatever, that these are the accepted standards that we're going to follow to keep the peace and make sure that we don't have interference.
Who makes the band plans?
Well, depending on the frequency you're talking about, it could be, ARRL in conjunction with some other groups. In a local area, there's something called a frequency coordinator, which I believe is one of the next questions. A volunteer frequency coordinator is a group of people who are eligible to own. A bunch of people who are eligible to have repeaters get together and elect somebody to basically decide what's going to be okay and what's not. There's typically a committee. They come up with standards for that particular region. If you're in Oregon, we can look up the thing called the ORRC.org, I believe, which is the Oregon Radio Relay Council, Oregon Region Relay Council. And notice what they publish. There you go. That's the band plan for 2 meters in the state of Oregon. There's another one for 70 centimeters. That is by agreement of people who use those bands frequently. That is how those bands will operate. Okay, if two stations end up on the same frequency, nobody owns a frequency. They have to decide who gets it. Maybe nobody gets it. Public service and emergency communications. ARES is the Amateur Radio Emergency Service. This is very similar to something called RACES, which is the Radio Amateur Civil Emergency Service. The only difference is that word civil. The fact that it's civil means that it's used for civil defense specifically, which involves the government. So ARES is a voluntary thing of people, equipment, and training that have registered themselves in order to help out in times of emergencies. RACES is the same thing except that that's specifically for civil defense. And that's run by a governmental organization. And that's actually, ARES is not in the rule book, and RACES is actually in the rule book. Net control, if we're doing a net, net is short for network. We do a lot of ad hoc networks, both simplex and over repeaters. And a net basically is a way for people to pass information back and forth. Net control is the person who is in charge of the traffic across the network. The traffic is information passing from person to person. Which of the following is standard practice when you participate in a net? The net control station is the traffic cop on a net. If you're going to talk, unless it's an emergency, you need to ask permission. If it's an emergency, you can blurt out something. But typically, if you don't have anything to say and net control is in charge, you don't say anything unless net control asks you to. That keeps the frequencies clear. Traffic. Traffic is formal messages passed by net stations. This could be how's the weather where you are. It could be what I just had a runner go past me at this particular aid station. It could be something about, we need a case of water. That would be formal message traffic. Good traffic handling. If you are passing messages from one person to another, you're typically going to write it down. If you are a participant in ARES or RACES, there's something called an ICS 213 form, which is a standardized form for formatting and passing of information. That's part of the whole incident command structure system that's used basically everywhere by emergency agencies. To ensure that voice messages containing unusual words are received correctly. Okay, so I'm going to do Kilo Juliet 7 Lima Charlie X-ray. And why did I do that? Because it's a call sign and it has a lot of letters in it, and they don't necessarily go together. So that is a way for me to unambiguously call out Sarah. If we have two people named Sarah, or for instance, or two Sarahs with different last names or different spellings, let's say we have an S-A-R-A and an S-A-R-A-H, and I want somebody to, know exactly which one I was talking about, I might spell it out phonetically. S-A-R-A-H, Sierra Alpha Romeo Alpha Hotel. We use phonetics all the time. It is encouraged to do so. It is important to understand and be able to use the phonetic alphabet, and that is the NATO phonetic alphabet, or ITU phonetic alphabet. Alpha, Bravo, Charlie, Delta, Echo. If you happen to be in the military or you happen to do dispatch for a police department or fire department, this will conflict with what is presently in your brain. The preamble of formal message traffic is how messages get from place to place, information needed to track the message. So that would be like the sender, the time, the date, message number, and the target. A check is basically the same thing that's sent with digital communications, where we use that parity bit. We add an extra 1 or a 0. In this particular case, the check is the number of words or word equivalents that we're sending. And we send that along with it. And if it's not a match, then someone will say, okay, I need you to repeat it because that number does not match what got sent.
Going back to the alphabet, where do you get that
Just look
information?
online. It's just it's the standard ITU phonetic alphabet. I
Okay,
mean,
thank you.
it's on Wiki, it's on, and I've never seen it not accurate. The key is that it's the one that's used all around the world, and all the letters were chosen so that people, even with accents from other countries, can still understand each other because English is the de facto language spoken on the air. All call signs, for instance, in Japan, there's a ton of Japanese stations on right now during this contest. They have English alphabet call signs. The English alphabet doesn't really exist that much in Japan, does it? I mean, they use kanji, and the same in China. But their call sign, for instance, I worked Bravo 4 Tango, Bravo Hotel 4 Hotel Golf. I worked them last night. The call signs follow the English letters. You'll also notice that if you travel a lot, the call signs on the tails of airplanes follow the same pattern of call signs. So, like a Japanese plane, the tail will start with a J. I saw recently, I think it was 5 Bravo, which was Cyprus. It was a Cypriot plane, and it had a 5 Bravo on the tail. So those were all those prefixes they came out at the same time because the aeronautical community and the radio community are both under the United Nations. So they did them at the same time. They adopted them together. When do the FCC rules not apply? And the answer is never. However, the rules only apply when the rules can be violated in situations when you're going to see this come up over and over and over. Immediate safety of human life or protection of property, like the dam is going to break. If the dam's going to break and there's no other way to get the message through, you can do anything you need to. But that's an important distinction. There's no other way to get the message through. There was a guy, I believe in Idaho or Montana a couple of years ago, and there was a wildfire, and he was trying to report it on the wildfire fighting frequencies, and he got on. He's a ham. He got on the wildfire frequencies and was trying to direct them, and he ended up getting something like a $30,000 fine because he could have just as easily picked up the cell phone and called the dispatcher.
Oh, wow.
And relayed it. He basically just took it upon himself to say, this is an emergency, and got on the air, and there were other ways to do it. And so he basically, in the process of doing so, potentially caused interference to the firefighting services. He thought he was doing the right thing, but it turned out he wasn't, because it really wasn't a bona fide emergency. If his house had been about to get burned down, yeah, probably it would have been okay, but it wasn't. So, all right, amateur satellites. The ISS contains a repeater on board. You need a technician class license or higher to contact it because it operates on VHF. If you have a technician class license, you can operate on VHF. Operating in UV mode, that's UHF up and VHF down. The most common UHF frequency is 70 centimeters. The most common VHF frequency is 2 meters. So 70 centimeters up and 2 meters down. They call it UV. Different modes that are used by satellites. FM for sure. I've done that. Also Morse code, also data, also single sideband. There are also coming down from, if you think about it, the ISS is a satellite. It's going around the Earth. They do periods where they send photos over slow scan TV over FM. So it's an image format. They send pictures of the ISS. They send all kinds of cool photos of, space exploration and things like that. Effective radiated power. Okay, so that's a combination of your transmitter power and the antenna gain. If you have too much effective radiated power, when it gets to the satellite, it will basically obliterate the ability of the satellite to receive other stations. So In order to modify that, you basically listen to the beacon. The satellite will be, because it's not just going up, it's coming down. You listen for yourself on another frequency, and if you're about the same volume as the beacon, you're probably not blowing the satellite's receiver away. What is a low Earth orbit satellite? Well, that's exactly what it's called, a LEO, for low Earth orbit. And the thing is about there's geostationary and there's low Earth orbit. Low Earth orbit satellites are fairly low altitude, and because of that, they're moving really fast. The ISS goes around the Earth about every 92 minutes. They have a lot of sunrises and sunsets every day. A geostationary satellite or geosynchronous satellite will basically stay above the same point all the time. If you look up and it's directly overhead, tomorrow it will be directly overhead. A satellite beacon contains information about the satellite. It is continuously transmitted or periodically transmitted, depending on the satellite. It might contain temperature of the onboard electronics, whether or not a particular transponder or sensor's working, things like that. Anyone can receive telemetry from a space station. You don't have to have a ham license because it's just receiving. To use satellite tracking programs, you basically have to go and figure out what the Keplerian elements are. Those are typically published for a given satellite, given the time and the date and the Keplerian elements of the satellite. That will allow you to figure out whether the satellite is approaching or moving away, how high up in the sky it's going to get. And from that, you can figure out whether or not you actually need to account for Doppler shift. Yes, Doppler shift. You know, that same thing that makes a fire truck sound higher and lower when it's going by? With satellites, they're moving fast enough that they actually cause the radio waves to change frequency slightly. If you don't account for that, you won't be able to make contact. Spin fade. As a satellite is rotating, it is tumbling in space. As it does that, sometimes the antennas will become obscured and go behind the satellite, and you will get a fade. Operating activities. There are a lot of ways to have fun with radio and get good at doing this. One is called contesting. All that noise that I showed you on that with all those Morse code signals, there's a worldwide contest going on right now. Make as many contacts as you can in a given period. In this particular case, it's 48 hours, and the goal is to make contact as many people in as many countries around the world in that 48-hour period. Because your job is to do that and make it nice and quick, you only send the information required as part of the exchange. It's just basically a way to have fun and become better at your craft. A grid locator. This is something that is included in, let's see, where's the grid locator? I know we showed this maybe once, maybe not. Grid square map. Okay, everybody see that? The entire planet is broken up into 2 degrees of latitude.
You're not sharing it.
Oh.
We don't see it.
Hold on. Oops. Should be, but isn't. Yeah, I need it. It came up in a different browser. Grid square maps. Okay, there we go. The whole world is broken up into 1 degree latitude by 2 degree longitude blocks. These are each given identifiers, 2 letters, 2 numbers. Right? You have the EM block, which is broken up into EM00 up to 99, DM00 to 99. This is a granular system, and each of those is actually broken up into 24 by 24 also. So 576 little sub-blocks for each of those little blocks. What it allows you to do is point an antenna, for instance, very, very accurately at another place. Montana is a pretty big state. Montana actually has something like 22 or 24 grids in it. And because it has so many grids, you might be, like in Idaho, you might be pointing your antenna north. You might be pointing it east. How do you know? The way you know is by looking at the map and figuring out what grid they're in, and that gives you a more granular view of where they happen to be. Okay, there we go. Well, that's a grid locator. Direction finding is a good way to find sources of noise interference. For a hidden transmitter hunt, which is a way to practice direction finding, you would use a directional antenna. Very often a little handheld Yagi, which is a beam antenna. So that would be like 3 elements, and the whole thing weighs like 3 pounds. You can make it out of a tape measure. If you're interested in looking something up, you can look up something called a tape measure Yagi. There are a lot of plans for tape measure Yagis. Everyone's got broken tape measures. And you can make a beam antenna that works for lots of different things for, I don't know, $5-10. Works really well too, even with a handheld radio. IRLP is the Internet Radio Linking Project, which uses amateur radio and mixes it with voice over internet. We're using voice over internet right now. IRLP mixes radio and internet. That's what VoIP is. Echolink is a system by which you supply your call sign and a copy of your license to the Echolink people. And what they do is they put you in the database as a registered user, at which point you can then use your application on your computer or on your phone. And if you have an internet connection, you can connect to any Echolink connected repeater anywhere in the world and use it as though you were in that geographic area. It's very convenient. Let's say if your local club has a net and you are out of town and you want to participate in the net, you just open up Echolink if the repeater is on Echolink, and you connect, and you operate as though you are sitting at home, and you're able to communicate with other people. Okay, let's see. IRLP. Some repeaters have IRLP nodes. To enter a node and hook up a repeater to the internet. DTMF, that is dual tone multi-frequency. If you look at your handheld radio, you will see that most handheld radios have a number pad that goes 0 through 9 and star and a few other things. If you're transmitting and you hit one of those, it will transmit touch tones. So those touch tones in the right sequence will open up the repeater and connect it to the internet. Okay, a gateway connects other stations to the internet. Oh, here we go, my favorite part, rules and regulations. Okay, the FCC runs amateur radio in the United States. The FCC is a party to the ITU, which is the International Telecommunications Union. That is the worldwide group of communications folks that decide around the world what is going to be valid and what is not. Basis and purpose of the amateur service, we talked about this. These are in the very first paragraph of Part 97. The very first one, saying what allows us to exist. Why are we here? The definition of a beacon is used for propagation, testing, or experimental activities. Let's say you put up a beacon on a mountaintop. It operates at different power levels 24 hours a day. And people around can listen for the beacon. If they hear the beacon, that means that there is propagation between you or wherever you are and that particular mountaintop. A space station is any amateur station 50 kilometers up or higher. When are you allowed to willfully interfere with another station? And the answer is never. Most radios are equipped with this thing called a tuning knob. You should get used to using the tuning knob. If somebody is annoying you, you can tune to another frequency. That's one nice thing about amateur radio. We can tune anywhere. We have an infinite number of frequencies that we can tune to in every band. Volunteer Frequency Coordinator, that is again the group that coordinates band plans and tells people what is able to be used where. The frequency coordinator is selected by the people in a local area that are eligible to own repeater or auxiliary stations. Okay, frequency allocations and power limits. For the most part, on the VHF and UHF bands, the power limit is 1500 watts. For the most part, unless you live within 100 miles of the Canadian border on 70 centimeters, and then the rules are a little bit different. On the 6-meter band, this is just memorization. You need to know what the 6-meter band looks like. You need to know what the frequency limits for all these bands look like because you're going to be using them. So, let's see if I open that up. Band plan. Here's the band plan, right? If you're going to be using these frequencies, you need to know what the limits are. 2 meters is 144 to 148. 6 meters is 50 to 54. These questions that are being asked become very, very simple because you know what those limits are. Okay. 146.52 is in the 2-meter band. A technician class operator has privileges on the 10-meter band on HF. That was something that we talked about yesterday. Okay. Phone operation on the 10-meter band, 28 megahertz is in the 10-meter band. Technicians can operate from 28.3 to 28.5. There is a single sideband section of every band, 50 megahertz and up. There's always room for single sideband. There's always room for Morse code. There are a couple of sections that are only for Morse code, and this is just memorization. Take a look at those answers. Those are the only bands that are specifically limited to Morse code. There is one band that is specifically limited to fixed digital message forwarding systems only. This came about as a result of United Parcel Service, believe it or not, and working with the FCC to trade 2 megahertz of our band for 1 megahertz of theirs. Doesn't sound like a very good trade, does it? You know why? Because it's not. That's another one of those reasons that the ARRL works really hard on Capitol Hill and at the FCC to keep us from falling victim to things like that. We are left with this 1 megahertz wide section from 219 to 220, which can only be used for this weird thing called fixed digital message forwarding systems only. I don't know anybody who uses this band. We had to give away 2 megahertz of perfectly usable band for that. But it's got to be in the rules. Why shouldn't you set up your transmit frequency to be exactly at the edge of an amateur's band or subband? Well, okay. So I'm going to show this picture, and okay, can everybody see that? What is the only real rule that exists with regard to the FCC about our signals on, let's say, the 2-meter band? Our entire signal has to be what?
Within the band.
Within the band. If you set it up so that your transmitter is on 147.999, is your dial frequency inside the band?
Dial frequency.
Dial frequency. But when you modulate a signal, what does it do? It takes up space. It takes up bandwidth. That bandwidth will cause it to spread so that your modulation sidebands are outside of the band. That is why we have to know how wide our signals are so that we don't get into a situation where we are going too wide and we are no longer in our frequency band. Okay, in some cases we are secondary, not primary. On the 70 centimeter band, we are a secondary user to the to the United States government. If they are using a frequency on 70 centimeters and we are interfering with them, we have to stop because we are secondary users. Above 30 megahertz with a few restrictions, the limit is 1500 watts. On HF, the peak envelope power, which is basically the peak power that you're transmitting, has to be 200 watts or less. I don't even have a 200-watt transmitter. Most people will never come across that unless they buy an amplifier. There are 3 license classes: Technician, General, and Extra. You may encounter people who have novices and advanced licenses, but you can no longer get those. Your license is good for 10 years. You can operate as soon as your license appears in the FCC database. You're allowed to have exactly 1 license. You can't have 2. And what makes it valid? Again, if it shows up as valid in the database, you are valid. Any amateur can select a vanity call sign. It costs $35 for the FCC to process a license grant. It costs $35 for you to pick your own call sign. So the only other thing about that is that your your call sign that you pick has to be valid for your license class. So this call sign, KF1XXX, this is a 2x3, it's called, because there are 2 letters before the number and 3 letters after. KA1X, that's a 2x1. W1XX is a 1x2. KA3MM would be a 2x2. N3FJP is a 1x3. Any technician or general class operator can get either a 1x3 or a 2x3. All the other formats are reserved for extra class operators. So if you want a really short, cool call sign, upgrade to extra. The grace period for renewal is 2 years. If your license expires, you just put the license, you send the form in, do it online, and you'll get your license back. You can't operate until it shows up as valid in the database. A club.
Scott, can you do it before it expires?
A little bit, yeah. I think within 3 months. A club must have at least 4 members, basically officers. A club call, this is actually... if the FCC is unable to reach you by email, this is really important. If they send you an email and it bounces back, they can, if they really needed to get a hold of you, they can pull your license. They can cancel it. If your email address is wrong in the database, they can cancel your license. You are allowed to operate from any craft in international waters that's registered to the United States using your United States call sign. Okay, let's see. Are you allowed to transmit indecent language? Nope. Nothing obscene, nothing indecent. There's always people out there who insist on pushing the First Amendment as far as they can. You will hear them if you are on the air long enough. When incidental to authorized retransmission of man-space communications, you can transmit music. That is the only time that you can transmit music. Most of us will never have that opportunity. We do not transmit music on the air. There are commercial stations that do that. The FCC and other agencies will talk to the ITU, and the ITU handles the request to say, people from your country can't talk to people from my country. There's actually no one in the world that the United States hams cannot talk to right now, even North Korea, if in fact there were ever a ham in North Korea, which there is not. Okay, when can you receive compensation for operating? If you're a teacher and it's part of your educational process. You can sell amateur gear on the air if it's not on a regular basis. In other words, you can, if it's specifically related to ham radio, you can sell it, but you can't run a business. There's other services for that. Broadcasting is intended for the general public. Do not ever say, I broadcasted, because that's incorrect. On the air, what you do is transmitting. It might be one-way transmission. We don't broadcast. Just a rule of thumb. If you want people to know that you know what you're talking about, you never use the word broadcast when talking about yourself. Under which of the following conditions are one-way transmissions permitted? If you're doing beaconing and stuff like that, it's fine. Morse code practice is fine. Broadcasting, not fine. However, there are times that we can actually participate in news collection and things like that, and there's that immediate safety of human life and protection of property. If that's true, all bets are off. So, what are we allowed to talk about? We heard a bunch of it yesterday. We are allowed to talk about ourselves, our families, our lives, our opinions, the car that we have, stuff like that. Okay, control operator. The control operator is in charge of operating the station, whatever that station is. The station can never operate ever without a control operator, which is somebody responsible. Even a repeater, which is automatic, technically has a control operator. The station licensee is the person who is responsible for the physical station. The station licensee will designate a control operator. Very often, like in this case of my garage, my station is I'm the control operator of my station. If the people are different, hold on. If the people are different, they're both responsible for what comes out of the station. Yes.
All right. Control operator, is that a person that is on duty all the time?
Yes.
All right, so they have to be there. Okay,
yep.
Thank you.
You cannot have a station if you have a club, you can't have somebody walk in without a license and use the club call sign. There has to be somebody there with the person who has the call sign.
To be clear, Scott, though, it is possible to be a control operator in a remote location.
Yes, and that is one of the modes of operation. So,
did they turn off the repeater then if someone's not standing there?
No.
That mean
so that's kind of a weird thing. Like I'm a control operator of a repeater. I happen to be a control operator. If something goes wrong, I have the kill code. I don't typically monitor everything because if I did, I'd be listening all the time, which I'm not.
So technically, they don't have to be awake to when it's on. Somebody asked that, and I thought I heard a yes.
For a repeater, no. Everything else, yes.
Another common use is a lot of people, especially with newer radios that can connect to the internet. They can go on vacation and then use a remote controlled software on their laptop to control their radio station at home.
I do it too. Okay, let's see. Okay, so under normal circumstances, why is this acting so weird? Under normal circumstances, when can a technician class licensee run an extra class station? The answer is never. So basically, the control operator cannot operate outside of their license class. The trustee of a station is basically responsible for the station itself and for picking out somebody to be a control operator. Okay, who can be the control operator of a station communicating through an amateur satellite or space station? If you're allowed to transmit on the uplink frequency, the satellite may have moved your signal somewhere else. You're not responsible for that. You're just responsible for the keying down and transmitting yourself. Control point, if I have a handheld radio, my finger on my push to talk button is the control point. That is the control operator function. Operating over the station over the internet is remote operation. I do that as well. There always has to be somebody at the controls, period. Automatic control, however, is repeater operation, and stations can operate in automatic control without somebody physically there. When are you required to transmit your call sign? And I know we have about 2 minutes to go. When are you required to transmit your call sign? Every 10 minutes and at the end. Notice, not at the beginning, oddly enough. You are not required to transmit your call sign at the beginning of talking. You don't have to ID yourself when transmitting to a model craft. In the United States, when you're identifying, you can use Morse code, or you can use a phone emission, which is voice. In the United States, you can have a conversation in Spanish, but you have to identify in English. When I go to Chile, I have to operate in any language I want. I have to ID in Spanish. Phonetic alphabet is strongly encouraged. If you're using tactical call signs such as race headquarters, is race headquarters a call sign? Yes or no? Nope. Okay.
No, no.
Race headquarters is not a call sign. It is a tactical call sign. How often do you have to identify? Every 10 minutes and at the end. You can also have self-assigned indicators. So I could be N7JI/W6, which means I'm in California. That is an unofficial thing. If I'm in another country, I would have to change my call sign based on their licensing requirement. A third party is somebody that you're sending information on behalf of or to. We do not have third-party agreements with every country. We have third-party agreements with some countries. You have to look at the list. There is a list maintained by the ARRL of about who we have third-party agreements with. If you plan to operate in another country, you should probably check with them as well. And finally, if the FCC knocks on the door, you have to open the door. They're the ones who are giving you your license. If they want to see something, they need to know what you need. They need to be able to come in and inspect your equipment. You might be interfering inadvertently with air traffic control next door. That would be bad. They need you to stop. They've identified your station as the culprit, and they want you to stop. So they knock on the door and figure out why.
Well done.
This is the second time that I've taken your class. First was during COVID, and I didn't make it the last time. So hopefully this time I make it because you're awesome.
Let's get you over the finish line, huh? I don't want to have to teach you a third time.
Yeah, you're an awesome instructor. So thank you.
Thank you. And I know the last part of it was just reading, but okay, I'm gonna stop.